to generate in situ this hypochlorite. So that will in turn oxidize this 1 mole of bromide to bromine. So you will get 2:1. 4:2 means stoichiometrically it will be 2:1. 2 bromides, 1 bromide, and you will get only the byproduct is the water and NaCl. This is the beauty of this process. So you don't have any other hazardous byproduct. Only aqueous NaCl. Even as those manufacturing bromine or alkali process, they set up only near seashore. So that can be even dumped into the sea because it's only sea is full of salt. So it can be directly discharged into the sea also without any purification. So for that we got another patent for this improved process of preparation of bromine reagent. This is a very simple setup. If you take that 5:1 intermediate bromide and they add alkali and just spurge through the chlorine gas, required amount of chlorine by just controlling the volumes. So that will in situ generate hypochlorite, so that will oxidize as bromide to bromine. So as I told, this reagent can be used either in the solution form or solid form. If you want to use in the same local where you are producing liquid bromine, in the same place if you want to utilize a bromide, you can use directly as solution. So if you want to transport means for other far distances, simply just evaporate, you will get the solid brominating reagent which is as good as, So this is like solid brominating reagent. As I told, it is a diver. If this BRS means brominating reagent for substitution reactions, we call it BRS. Wherever I use the term BRS, it is a brominating reagent for substitution reactions. BRA means brominating reagent for addition reactions. We can use both for addition reactions, substitution as well as oxidation reactions. Okay. So that 2:1 bromide, if you add acid, required acid, any acid, you take nitric acid, sulfuric acid, HCl, hydrochloric acid, whichever is the cheap for industry. Industry always looks for the economy. Whatever the cheap acid, sulfuric acid is the more cheaper. So we use only hydrochloric acid because sodium chloride is the byproduct. So it can be easily evaporated to obtain the sodium chloride back, or you can just discharge it to the sea also. We use the hydrochloric acid. 2:1, it generates only selectively hypobromous acid, which is a very good species, can be used for diverse reactions, maybe substitution reactions, addition reactions. If you use addition reactions, you will get the bromohydrin starting from olefin, and if you use for alcohol, it will oxidize this alcohol to aldehyde. The same reagent can be used, this one BROH, for variety of applications. So that selectively generates hypobromous acid, which has been proved through UV visible spectroscopy. It absorbs at 360 nanometers. Okay. So for generation of this hypobromous acid, HOBr, it requires only specific pH. Only we should maintain the pH around 4. If it goes beyond 4, means if highly acidic like 1 or 2, it again disproportionates into other various species. So the maintaining of this pH for this hypobromous acid is very important, so that you can get selectively hypobromous acid. Okay. So nowadays there are hundreds of commercially available brominating reagents available in the market. Maybe starting from liquid bromine, which is very classical, maybe N-bromosuccinimide, which is another important classical reagent. It can be used for the bromination as the same. But maybe some other, these are other brominating reagents, use vanadium salts, maybe zeolites, some other salts like that. But as I told, there are hundreds of reagents available commercially, none of them are viable for commercial production. Only for academic it is okay. So to overcome that, maybe as I told, still industry or academia, they are using only liquid bromine, maybe lack of better alternative source for this bromination processes. So to overcome that, as I told, we have developed this green bromine process, whereas if you take any array for substitution reaction, generate BROH, room temperature, so you will get the substituted organobromo compound. The byproduct is only water. If you use NaBr, NaBrO3, only sodium chloride is the byproduct. You can use any KBr, KBrO3 or NaBr, because sodium hydroxide is cheap, so we use only alkali as the sodium hydroxide. So these are some of the representative examples of aromatic substitution reactions with our green brominating process. Like phenol, you can see variety of phenol. When we brominated this phenol with monobromo bromination with one equivalent of phenol, we obtained 81:19 ratio of para to ortho, because it is very difficult to control 100% selectivity. So we obtained total yield 91% with the para ortho ratio, 81:19 ratio. And 3 equivalent of the reagent, tribromophenol, 4 equivalent of reagents, tetrabromo hexadienone, which is again a very good reagent for the bromination of aromatic substrates. So the beauty of this molecule, tetrabromocyclohexadienone, is that if you can use for bromination of amine, selectively you can just get a monobromo, whereas with respect to aniline, 4-bromoaniline you will get with a high selectivity, and again the byproduct will be the tribromophenol, which is a water soluble. If you add alkaline, so you can get back the sodium salt of tribromophenol, further acidify it with our reagent, you can get back this again tetrabromocyclohexadienone. It can be used without any alkali solvent. You can brominate the aniline to bromoaniline, selectively monobromo, and you will get back this again. You can regenerate this tetrabromocyclohexadienone with our reagent. So this is the beauty of this. As I told, this is the molecule which we prepared tetrabromobisphenol A in 92% yield. This is not only gram scale or lab scale, we have demonstrated this to industry at pilot scale as a part of the technology transfer. Maybe you can use, it can be used even for phenols, naphthol, alpha-naphthol, even beta-naphthol, mono and dibromination. Variety of substrates can be brominated with our reagent. These are the representative amines, aromatic amines. Maybe hydrocarbons like anisole, naphthalene, even benzene. For benzene it requires temperature, 70-degree temperature is required because we are not using any metal catalyst, only bromide salt. So only for, except benzene, all other substrates are carried out at room temperature without any heating or without any catalyst. So this, again as I told, this N-bromsuccinimide also you can prepare with our reagent with 78% yield at room temperature. So again anylides, these are the examples. So this is the proper mechanism how our reagent works for substitution reactions. So as I told, it's not only for aromatic substitution, even for active methylene compounds like 1,3-diketones if you take, selectively you can obtain the monobromo active methylene compound. So these are the representative examples. It may be that maybe cyclic ketones, maybe aliphatic open chain ketones you get selectively with a very good yield at room temperature. So even if you take chloroacetic acid, if you use our reagent, you will get monochloroacetic acid. This is the beauty of this reagent. So you can prepare at room temperature in lab scale. But not only aliphatic active methylene compounds, if you take toluene, if you use our reagent, for the toluene it requires dichloromethane. Any chlorinated solvent, either chloroform, dichloroethane, dichloromethane, chlorinated solvents only it works very well for this benzylic bromination. So if you use one equivalent, you will get the benzylic bromide. So these are the representative examples of variety of substituted toluenes like nitrotoluene, maybe 2-chlorotoluene, bromotoluene. So you will get the variety of benzylic bromination. If you use xylenes, for the xylenes, if you use two equivalent of the reagent, because if you take either maybe para or ortho, meta, so you will get the corresponding alpha-alpha dibromo corresponding product in the case of xylenes also. Okay. So very important product is actually selective contact herbicide. It will kill only unwanted weeds which are disturbing or maybe decreasing the crop yield in the pesticide control. So this is the bromoxynil is a very important pesticide. So this product also we have prepared quantitative yield. So here there is no organic solvent also used in this particular process. This phenol, cyanophenol, maybe you can call it the 4-hydroxybenzonitrile also. If you take this at heating mild conditions, 60 degrees, it is soluble in water. So if you use our reagent, bromide salt and acid, so you can get the product. When at 70 degrees, it is phenol is soluble in water. After the bromination, the product becomes solid, which is insoluble in water. So simple mechanical separation and washing with water, we can get the quantitative yield of this dibromo 4-hydroxybenzonitrile, which is a contact herbicide. There is a generic name is called bromoxynil. So this with quantitative yield more than 99% GC purity we have obtained as a part of our technology. We have also transferred this and demonstrated even at kg level. So it works very well without any disturbing, and the purity also very good, more than 99%. Simple mechanical filtration and water wash. You will get the very good quantitative yield. So 99%, more than 99% is without any purity. So we have transferred this technology and we got the patent for this molecule, particularly only for this molecule. That we given to the published. Not only aromatic aliphatic substitutions, the reagent, it works even for heteroaromatic compounds like you take thiophenes, pyridines, aminopyridines, maybe naphthalines, naphthyridines. still it works very well for aromatic heterocyclic brominations also. So these are representative examples for 2 amino pyridine derivatives, maybe 3 amino pyridine derivatives, 1,8 naphthalene. These are the very good ligand. Still we can prepare this monobromo. If we take 2 equivalent of our reagent, we get dibromo. Maybe here this is the ratio which is inseparable. By NMR ratio we have obtained this. Thiophenes also, the ratio is this mono and di we obtained, but total yield is 90%. And the ratio of this mono and di was obtained because these are inseparable ratio geoisomers. So this is again probable mechanism for heterocyclic brominations with our green bromine process. So maybe it is a very well established. Another important intermediate is the 4-nitrobenzyl bromide in the drug, one of the drug manufacturer in the industries in Gujarat. Based on our publication, they approach us, they are interested with this 4-nitrobenzyl bromide. It is the intermediate they require this to prepare with our reagent. So we have developed the process for this. It's a very again beauty without any column separation distillation. Simple this centrifuge, we can get quantitative yields of this 4-nitrobenzyl bromide with again 98% purity based on the PNT 4-nitrotoluene starting material based on this. We obtain 98% yield. Simple cold centrifuge. Here the byproduct is the dibromo. Along with the 4-nitrobenzyl bromide, some amount of dibromo formation was observed. Sorry, this one. So this can be just by centrifugation. This is a liquid, this is a solid. Just by cold crystallization, we obtain this quantitative yield with more than 98% purity also. So this we got patent as well as been published. Okay. Another important intermediate, this actually is that 4-nitro dibromo aniline. It is a dye intermediate. All the dye manufacturers use this bromo derivatives. In again one of the Surat industry, they approached this. They wanted to develop this process using our green brominating reagent. So we have developed this process. Again, it's a quantitative yield with our reagent at room temperature. So finally, they did not take our process because they said they are very compatible with liquid bromine. Even our process, as it requires only bulk volume, no organic solvent, but they don't want to change their existing liquid bromine. They are using sulfuric acid and liquid bromine process. Finally, they did not take our technology, but we have developed the process. Finally, we just published also. So when we sent it for publication, the reviewers asked, you are only demonstrating and the process is very good, can you extend this methodology to other substrates also? Even though we have shown this in our previous publications, based on the reviewers' comment or to satisfy the reviewer, we have in the other bromo compounds also we have prepared here also using this technology. And eventually, say for this anilines, we have to maintain a little bit acidic in nature. The solution, aqueous solution will be little bit acidic because the amine is easily form the salt. 0.5 equivalent of acid will be used excess. That after the filtration of the product, that acid can be recycled aqueous till up to, I think you can carry out maybe number of cycles. Up to 5-6 cycles we have performed, still it gives very good yield without affecting the purity and the yield of the product. Only water can be recycled. Okay, the other, as I told, this is used for the diverse applications, this reagent. This is for brominating reagent for addition reactions. So if you use any olefins, so use that intermediate 5:1 as I told in my beginning slide, 5:1 intermediate and add acid in situ along with this olefin only with the water. So it will generate in situ liquid bromine. That means it is a Br2 will be generated in situ. So that will add across this double bond. You will get dibromo corresponding alkane. If you start with alkene, you will get dibromo alkanes. If you start with alkyl, you will get dibromo alkene as the product with in situ generation of this one. So this is called the BRA, brominating reagent for addition reactions, and this is for BRS, brominating reagent for substitution reactions. So even this reagent can be used for addition reactions. As I told you, will get the bromohydrin, this reagent. Even for oxidation also we can use this BRS. So that means it will get oxidation of corresponding substrate and maybe to oxidized product. So this can be used for addition reactions. These are some of the representative examples for brominating reagent for addition reactions. If you take any olefin, you will get dibromo corresponding alkanes. If you take cyclic trans, you will get the trans dibromo, which is very useful. If you take any olefin like stilbene, so you will get the DL isomers as well as SO in the case of cis and trans isomers. You can see that yields obtained are very quantitative yield in many cases. without any cooling or heating, only at room temperature reactions were carried out with this reagent. Again, if you start with the alkynes, you will get dibromo-alkenes. Again, addition reactions, in situ generation of the elemental bromine for the alkyne. If you take phenylacetylene, you will get this styrene dibromides, and these are the other representative derivatives. Maybe other, not only simple alkenes, even extended alkenes also it works very well. These are again representative examples. So finally, we just use this reagent for visinal functionalization. So this here, in this case, we have extended towards iodination also. Instead of simple bromination, so you can use maybe even you can use bromide-bromate or iodide-iodide. You will get the corresponding halo derivative, iodo or bromide derivatives. Use bromide-bromate and acid. If you only reaction you carry out in water, so you will get corresponding haloid rings. Corresponding, if you use bromide-bromate, you will get bromide ring. If you use iodide-iodide, you will get iodide ring. And if you use methanol as a solvent, here, so you will get this corresponding halomethyl ethers starting from the one substrate, and instead of here, if you use acetic acid without any organic solvent, acetic acid plays a triple role here. It acts as a solvent, acylating agent, as well as a proton source to generate HOBr from bromide-bromate intermediate. So you will get corresponding haloacetate, halomethyl ether, halohydrins. So these are the again definitive examples for bromomethyl ether, bromoacetate. So you can, based on your desired requirement, you can start from the corresponding substrate, you can obtain corresponding halohydrins, maybe halomethyl ether or haloacetate. So the same methodology has been extended to one of the rose oxide, it's actually the perfume used for the synthesis of this rose oxide. As we use iodide for this olefin citronellol, so starting from this we can obtain this iodohydrate corresponding halomethyl ether, under methanol if used as a solvent. You get methyl ether. It can be then further conjugated to basic hydrolysis. You will get this internal olefin. Further hydrolysis of this and cyclization, we obtain this rose oxide starting from iodomethyl ether. Citronellol, we get the rose oxide with our process using our reagent. So we know that this reagent works very well for even addition reactions, substitution reactions. So one of the other perfumery industry, the soap manufacturers, they use this beta bromostyrene to give us a very good flavor. So we wanted to prepare this beta bromostyrene starting from this bromostyrene bromohydrate. So selective dehydration we tried with the various acids. So unfortunately we did not get the dehydration product beta bromo. Instead of that, it undergone intermolecular condensation with elimination of the water. We obtained this ether. So we did not get this desired beta bromostyrene. But however, this is also very important molecule, so we have converted to the crystal structure. Further, we continued our effort to just obtain selective dehydration of styrene bromohydrate to beta bromostyrene. So then we succeeded by using H-beta gulate as a catalyst. It acts as a proton source, and also the catalyst can be recycled and reused. Selectively, it will dehydrate only this water. You will get this beta bromostyrene. And these are ratio of cis and trans ratio, or the ratio of 25:15 ratio, and up to 75% isolated yields of this only for beta bromostyrene. So these are the representative beta bromostyrenes with the selective dehydration. This bromohydrine can be prepared starting from styrene using our BRS addition reaction. You will get the bromohydrine. So if you subject that for dehydration, so selectively we can obtain this beta bromostyrene using H-beta gulate. It can be also recycled, but there is a slight decrease in the yield maybe after the reaching of this catalyst, but after many cycles. As an outcome of this bromination process, as you know, whatever the process we are being in CSIR, which we have to take up the societal problem, and whatever the technology you develop, it has to be transferred to the end user. That is the CSIR main goal. So to satisfy that, we have transferred these 6 molecules, 6 processors for the industry, for the bulk scale manufacture. This is a tetrabrom, this one, as I told you, is a fire retardant. This is again bromoxynil selective contact herbicide, and intermediate 4-nitrobenzyl bromide. Bromobenzene is a very good intermediate for variety of reactions. Bromosuccinimide, this is the di-intermediate tribrom only. So we have transferred this technology to Alchem industry in Kutch, Gujarat. So they are manufacturing. Also we have done this invited review and organic synthesis for this bromination process. This is the overall process of bromination process, starting from bit ton to final product. So if you take this Mithun acidification, you will get this transient bromine, which will be further added alkali and this further chlorine gas. You will get this intermediate 5:1. So we did not go in this process to recover the bromine. We further added alkali and we adjusted this 5:1 to 2:1, where you add aromatic substrate and again acid. You will get the corresponding organobromo compound with the aqueous NaCl as the byproduct. This is the overall presentation of this bromation cycle. So we have seen that substitution reactions and addition reactions. Let us see some of these oxidation reactions. As I told, this reagent is a very wide applications. Can be used for substitution, addition, even oxidation. If you use this reagent for oxidation, corresponding alcohols like benzyl alcohols to benzaldehydes. If you use benzyl alcohol, you will get the benzaldehyde. If you use secondary alcohol, cyclohexanol, you will get corresponding ketone. So this is a very good reagent. But however, here we have what we observed, but it requires a stoichiometric amount, BROH, but bromine is not part of the product. Only it will again end up as a HBr. So again there is a drawback. So it does not work for aliphatic alcohol. So we obtained only corresponding monoester in the case of aliphatic. Only benzylic alcohols it works very well. Benzylic and secondary alcohol. So to overcome, as I told, that bromide is not part of this process. This is again it will end up as a HBr. So to overcome that, we again reduce the stoichiometric to catalytic amount of this bromide. We need only 33% of bromide, catalytic 5 more % of bromide. So still we can oxidize this benzylic alcohol to corresponding benzaldehydes with catalytic amount of bromide. So this shows that it requires catalytic amount of bromide. So if we don't use the catalytic bromide, only bromide, the corresponding conversion will be less, corresponding acid formation is more in the case of without bromide. If you use only bromide and acid, so bromide is a strong oxidant, so it oxidizes aldehydes to acid. If you use catalytic amount of bromide, selectively it generates BROH species, that is a very selective and mild oxidant, so it will end up with only aldehyde state. So that is the reason catalytic amount of bromide is required. So not only alcohols, as I told, so if you use even sulfides, so you will get sulfoxides with our reagent. If you use the thiols, thiophenols, you will get corresponding disulfides. So these are the representative sulfoxides as well as disulfides. It can be used for a variety of oxidation reactions, as I told, benzylic alcohols, maybe secondary alcohols. This is the overall scheme how we can use this recycle, this aqueous effluent for oxidation reaction. Bromide is not part of the product. It will end up as an HBr. So that HBr further can be oxidized with hypochlorite, as I have shown in my previous slides, which again stoichiometric, it generates bromide to bromate 2:1. Further oxidation, so you will get this corresponding cycle. So the aqueous effluent can be recycled for oxidation processes. So without any metal, you can just use it. When we submitted the manuscript for publication, always we received some comments from the reviewers. So bromate is not safe, it is a carcinogenic. So most of the reviewers, they used to say. So again we reduce that bromine instead of stoichiometric to catalytic. If you use only 10 mole, 15 mole percent, 10 mole percent of together, bromide together, only 10 mole percent of bromide, and with respect to the substrate, only acid. So still we can just get the oxidized product like corresponding alcohol, aldehydes or ketones. So still these are again reducing the stoichiometric bromide to only catalytic. Still we can obtain this oxidation product. So this is a mechanism how it works for oxidation reactions. 5:1 bromide generate the bromine, bromine. Bromine in the water disproportionate to hypochromous acid and HBr. So that if you generate HBr for oxidation of this benzylic alcohol, you will get aldehydes or corresponding ketones. So this is how it works. So only together, only 10 mole percent of bromide salt, and acid is again catalytic 15 mole percent of acid, so that you will get corresponding aldehydes or ketones. So again, to completely avoid even bromine, so we use only catalytic amount of hydrobromic acid, even which is commercially available. So you can use even HBr and H2O2, but still you can get this oxidized product starting from, because that generates HOBr species. Bromine in the water, we will get BROH species, so that can be again used for oxidation reactions. So still you can use this. This is a mechanism how it goes stepwise. HBr and H2O2 generate BR2 in water, so it is disproportionate to BROH, and this is actually the reactive species. BROH, we call it as hypochromous acid, which is very selective reagent. for again the rate of reaction, so that you will get corresponding benzylic alcohols to benzaldehydes, or again the same secondary alcohols to corresponding carbonyl compounds. So very good yields. So instead of using benzylic alcohols and secondary alcohols, we thought what happens if you just, in earlier cases we have seen, if you take toluene, we ended with the benzylic brominations. So when we extended this, still when we use 3 equivalent of the reagent, starting from the toluene, so we can obtain the corresponding acid, corresponding benzoic acid, starting from methyl arenes. This is a very important process. Again, just to use 3 equivalent of reagent with toluene, you will get corresponding carboxylic acid. So instead, here there is no water, organic solvent is used. So only water you will get benzoic acid. If you start with organic solvent, you end up with only again benzylic bromination. So to avoid that, we perform the reaction only in water. These are the representative carboxylic acid, aromatic carboxylic acid. So you will get the very good yields of this corresponding. What is this stepwise process? It go in this way. Starting 1 equivalent of 3 equivalent is required, because if you start with the toluene, methyl arenes, initially you will get the benzyl bromide. Again, benzyl bromide will undergo oxidation, you will get benzyl alcohol. Further oxidation, you will get the benzoic acid. So this is how it works. This is the mechanism, bromide. Again, here for the oxidation reactions, bromide is not part of the process, part of the product, so that HBr can be again recycled for the oxidation. This is how we have recycled this 4-nitrotoluene to see how it works. Even up to 3 cycles, we can obtain with really good yields of the corresponding benzoic acid by recycling aqueous HBr after the oxidation process. These are the again the starting. We know that the toluene oxidation to benzoic acid, which goes through stepwise mechanism. Initially, it forms the benzyl bromide. Just by benzyl bromide refluxing only in water, it will form benzyl alcohol. Again, benzyl alcohol will undergo oxidation. So then, instead of using toluene or other such benzyl alcohol, again we started with the benzyl bromide. If we start with the benzyl bromide, so you will get corresponding benzaldehyde with again with the HBr and H2O2 process. It's only water, no any organic solvent is involved here. So only you take water and benzyl bromide, reflux and add H2O2 at room temperature. After the reflection, you add H2O2 only at room temperature. The refluxing is required to break this CBr, convert into benzylic alcohol. That happens only in water medium. If you take any organic solvent and reflux, it does not undergo benzyl bromide breakage. So that is again important observation which we have observed. So this is how it goes. Benzyl bromide, if you reflux in water, you get benzyl alcohol. Again, benzyl alcohol is used of BROH to get aldehyde. If you use another equivalent of this BROH, aldehyde will further undergo oxidation. So yeah. So that we know that benzyl HBr, either you use HBr or bromide, green brominating reagent. So we can get the corresponding benzyl bromides or benzylic benzaldehydes or benzoic acid. Then we thought instead of using only oxidation process, why can't we extend further? So then we used this HBr and methanol. So we can get corresponding oxidative esterification of methanol. Maybe corresponding aliphatic alcohol with benzylic alcohol. Still be this obtain very good yields of corresponding methyl esters of this benzyl alcohol. Not only benzyl, even other heterocycles like methanol, thiophene also it will work. Cinnamic acid derivatives, other pyridine derivatives also work. So this is how it goes through the radical mechanism, which converts through the tempo. Tempo will trap the adduct radical formation. So that shows that the reaction goes through the radical mechanism for this oxidative esterification using HBr and H2O2 process. So we can this brominating. So this is the mechanism for the oxidation. How that benzylic alcohols will undergo oxidation with benzaldehyde. HOBr will exist in dissociated Br plus and OH minus. So this BROH reacts with this alcohol intermediately, and we get this intermediate. Dehydration will get again highly unstable intermediate. Further, that elimination of HBr from this intermediate, so we will get the stable aldehyde. This is how the oxidation process occurs. Okay, we have seen other oxidation, substitution, addition, oxidation reactions. So let us see some of these oxybromination reactions. So as I told, it can be used for even oxybrominations. If you take a toluene, styrenes or any olefins, if you take one equivalent of our reagent, so you will obtain only bromhydrine. This bromhydrine, if you take any olefin and one equivalent of our reagent, bromhydrine, If you use two equivalent of this reagent, they are OH with respect to the corresponding olefin, so you will end up with only oxybrominated ketones, which is very good intermediate, which is alpha bromo ketones. In one step, you can prepare this alpha bromo ketones starting from olefins at room temperature. So only we have to use again two equivalent of the reagent. So you will get here also completely atom efficiency is there. If you use one equivalent, you will get alpha bromo, and if you use two equivalent, you will get mixture of chloride. One equivalent is required for the bromohydrate and another equivalent for the oxidation. So another equivalent is not required, only 0.7 equivalent we can oxidize the secondary alcohol to ketone. So these are the reference. Here it works very well for even aliphatic olefins, long chain alkenes. So you will get corresponding alpha bromo ketones, terminal ketones, which are very good intermediate for organic synthesis. Still we can, all these reactions we can just obtain with our agent at room temperature. So again, if you take styrene and use BRA, you will get dibromo. This can be again subjected, you will get the bromohydrate. The same intermediate along with HBr, if you add H2O2, again you will get the bromo ketones. To this intermediate, if you add base, so you can obtain even hydroxide. Starting from one intermediate, so we can obtain the desired molecule, maybe dibromo, bromohydrins, epoxides, alpha bromo ketones. These can be obtained from starting from any olefin, alkenes, simple alkenes. So again, instead of using our reagent, you can use HBr-H2O2 for synthesis of alpha bromo ketones. So why we shifted from our green bromatic reagent to HBr? Always we used to receive comments from the reviewers. Bromate is not safe, it is very carcinogenic to handle in Europe. So then we have shifted from bromate to only HBr. So you can use HBr and H2O2. Still you can get these type of products, alpha bromo ketones or maybe dibromo compound or corresponding oxidation products also. So then we use HBr also. One equivalent of HBr is styrene. H2O2 at room temperature you will get bromohydrate, quantitative yields. And if you use 1.7 equivalent of HBr, still you can get this bromo ketone, alpha bromo ketone at room temperature. So these are again the representative examples for this bromohydrates using HBr and H2O2 process. So you will get these bromo ketones. So if you use olefins, any alkenes, so you based on the amount of reagent you are using, you will get either bromohydrates or bromo ketones. Suppose if you start with alpha bromo means vinyl bromides, if you use again our reagent or HBr-H2O2 process, you will get a rearrangement occurs. This is the oxidative rearrangement. This bromide will be shifted to terminal bromide, and this carbon has been oxidized with H2O2. So here again, if you start with vinyl bromide, you will get oxidative alpha bromo ketone. Or if you start with alkynes, even the same reagent, stoichiometric reagent, so you will end up with all dibromo ketone, alpha dibromo ketone, even starting from alkynes. Either if you want, you can use our reagent or maybe HBr-H2O2. Remember, HBr also is not cheap compared to bromide salt. HBr is more costlier than liquid bromine. So that is the reason industry needs always very economic process. So you can start with the bromide salts, which is very cheap, commercially available, and also that is the intermediate from the bromine recovery processes. We are not using pure bromide salt. It is the intermediate where bromine manufacturers producing that intermediate, and further acidification they will obtain the liquid bromine. We are not using that pure bromine or maybe the pure salts, which is very cheaper than even liquid bromine. Compared to it is cheaper because it is intermediate. So that is the reason we are using only the intermediate 5:1. This is the proposed mechanism for the rearrangement of vinyl bromides to alpha bromo ketones or alkynes to dibromo ketones. So this vinyl bromide, if you start with, if you use our reagent, so it forms in situ this bromonium intermediate cyclic, remember, which is very unstable, and it again undergoes bromohydrin formation. Compared to this intermediate stable. Further, both are this carbon, hydroxy and bromo are unstable. Further, it undergoes oxidation, elimination of HBr, so you will get the bromo ketones. This bromine, again, if you use H2O2, liberated bromine can be used further to get dibromo ketones here. So if you want to stop only alpha bromo ketones also, we can stop. It undergoes oxidative rearrangement because this carbon and this carbon, both bromide as well as OH are unstable. So this we have confirmed through the studies. Only that bromide will undergo shifting from here to here. So only catalytic amount of bromide, it will oxidize as this, we have alpha bromo ketones, vinyl bromide. And also this one equivalent of this reagent with alkynes, You get intermediate, again unstable intermediate, elimination of the again water, further in one equivalent addition you will get this dibromoketone. That may go either this intermediate or this intermediate, but finally we end up with alpha-alpha dibromoketone starting from even either alkenes or alkynes. So based on that. Okay, we have prepared a variety of bromo compounds and even demonstrated to industry. So further we thought of whether we can just beta bromostyrene selective dehydration, we thought whether we can obtain selective dehalogenation of aromatic compound. So when we tried with a variety of other catalysts and reagents, so finally we just observed that again that H-beta Juline will selectively dehalogenate only at alpha position, which is the reverse of the reactivity. If you want to bromination, alpha bromo naphthalene you will get first, 1 bromo 2 naphthalene. In the case of dehalogenation, it's exactly reverse. It will dehalogenate first this bromination and you will get corresponding bromo product. If you take a tri-bromo and tri-iodo phenols, selectively para dehalogenation takes place. This is the beauty of this process. We are unable to how it acts. Finally, the mechanism we don't know. But only other sources will not work. H-beta Juline does this job, selectively dehalogenate. Remember this introduction of this either ortho directly is very difficult. So with our process, you can prepare tribromo and use H-beta Juline and sodium sulfite and methanol refluxing condition. Selectively dehalogenation takes place at para position without disturbing even either ortho position. Either maybe iodo or bromo, so you will get selectively. And if you take tribromo 2 naphthal, selectively as I told, only first will prepare will, it is exactly reverse of the reactivity. If you take one equivalent bromination, first bromo will go here, and second bromination will go here. The dehalogenation is also reverse. First dehalogenation occurs here. So in addition to the dehalogenation, we observed this formation of this coupling product 11% during the dehalogenation process. Instead of H-beta Juline is also commercially available, but for the as we have been working on the most economical process, we thought still why can't we use some other proton source like potassium hydrogen sulfate, again it is very cheap compared to H-beta. We use this also. This also will work very well for the selective dehalogenation. We can use tribromo, triiodophenol, use potassium reductive dehalogenation. You will get again the same type of product. So you will get selective dehalogenation of para position only without touching either ortho position. Both sides are halogen will retains. Even if it works selective dehalogenation, so it is not good. Then we thought whether we can extend this for selective dehalo substitution. So initially we thought we use some other electrophile. When we use nitric acid as an electrophile here, after the just dehalogenation, so still we obtain this corresponding nitro product. Actually nitric acid acts as electrophile, undergoes after the dehalogenation, nitric acid will just will get the corresponding substitution also. Take the tribromophenol, only use nitric acid diethyl ether as a solvent at room temperature. Only after 15 hours you can just obtain this dehalo substitution products also. These are again some of the representative examples. As we prepared this tetrabromohexenol A, this also be subjected for the dehalo nitration. But again we will get di-nitro substitution corresponding with the dibromohexenol. It's also very good intermediate. This can be again reduced, can make even aminophenols in one part that can be used as a synthone for the synthesis of variety of organic processes. By this way also, so you can just prepare maybe variety of bromo product, oxidation. You can use this reagent for oxidation, maybe oxybromination, thiol oxidation, disulfides oxidation. So maybe variety of reactions you can use. So again, this is the mechanism for dehalogenation, how it works, dehalonitration. Nitric acid, it will exist only 5% as a nitrogen ion, and only this very less percent, 4% of this electrophile acts as electron substitution during this elimination of this para. Only you will get, even we are using excess of nitric acid, it does not touch with either ortho position. Selective only para position will be dehalogenated and undergoes the corresponding substitution reaction. So this is the final summary and conclusion of this bromination process. We have seen that starting from bromination even its preparation, it's a very safe. It will actually compared to liquid bromine, it's very safe, easy to use, transport and handling. And the brominating reagent generates the reactive intermediate BRO species, which is a very versatile reagent we can call it. Or even you can use for oxidation substitution reaction, for alkenes, aromatic, active methylene compounds, oxidation of styrene to bromhydrine or bromoketones. and maximum atom efficiency. There is no byproduct HBr formation was observed as the case of liquid bromine. If you use liquid bromine, 50% HBr will form. So if you use our reagent, selectively generate isobromous acid, which is 100% atom efficiency, which is required for industry. They don't want to lose any bromide or any atom economy. So it's a very 100% efficient. No formation of byproduct. Byproduct is only aqueous NaCl. Sodium chloride is a byproduct. It can be discharged into environment without any treatment. Or by solar evaporation, we can also recover the sodium chloride also. So only water is the byproduct. Okay. The brominating reagent can be obtained, as I told, it can be obtained either solution form or solid form as per the user convenience. Those who are producing at the local place and local utilization, they can use a solution form, or for the transportation, so it can be just water evaporation. You will get the, as I showed, the solid reagent. Both the brominating reagent for addition reaction and substitution reaction, it can be obtained either solid or solution form, and operates under ambient conditions. Except for bromobenzene, all the reactions were carried out at room temperature, ambient conditions. Only bromobenzene, it requires a little bit, because it is inactive substrate, it requires some heating to activate the aromatic side, then only you will get the bromobenzene. Except bromobenzene, we have prepared more than, I think we can count more than 200 molecules with our process. So all are at room temperature, ambient conditions. So that's how this is the, finally I acknowledge my students and also the funding agency for which we have undertaken. And thank you for your patience. So any questions, I am very happy to answer.
Thank you very much, sir. Thanks for your well knowledgeable lecture. Is there any questions?
Yeah.
Instead of nitric acid, can you use something so that your bromine is then not going to lowest? Bromine can be used too.
The simple reason we use nitric acid, nitrate is a very good electrophile. So that can be substituted at room temperature at only diethyl ether. You can use other, we tried other electrophiles also, but it does not work for this dehalonitration in one part. So maybe if you take separately dehalogenated, then it may work. Only very few electrophiles we tried, but it didn't work. Even alcohols or sulfur acetylating agents like acylation, we tried, but it didn't work. Maybe if you continuously try some other investigation, may be possible. It may work. So I suggest maybe for the faculty, when you have maybe MSc practicals, or maybe you may come across some liquid bromine usage for a practicals MSc. When I was studying, we fed up with liquid bromine for preparation of MBS in the lab scale. So instead of that, liquid bromine, whatever the bromo products is there, better you can use pure salts. You can use NaBr and NaBrO3, so that you can avoid the handling of liquid bromine. Still, you will get the good result with safe reaction. You can carry out the reaction in the open bench for MSc practicals, maybe even BSc also, so that you can just do. Some of the Delhi University, some professors are practicing this our reagents, because we have presented in many green chemistry conferences, so they are using our process for particularly for MS, undergraduate and postgraduate as a practical example. So you can also try for this reagent. You can use pure sodium bromide, sodium bromate, and 3 equivalent of acid, HCl, for the bromination reaction. It can be used for even oxidation of alcohols to aldehydes, benzylic bromination. For academic purpose, without any intellectual properties, you can just use to prepare for academic purpose.
Thank you.
So, is there any other green bromine other than bromine hydroxide?
Brominating reagent. What you are asking?
I mean to say that is there any other green bromine other than bromine hydroxide?
Green bromine process. I have showed.
In your paper, you are using bromine hydroxide as green bromine.
Bromo, hypobromous acid. Other than, you can use HBr H2O2 also to generate the hypobromous acid. So there are variety of reagents available. So you can use liquid bromine. See, ultimately in aqueous conditions, if you use the bromine also, you will get HBr and BROH. Again, their atom efficiency is only 50%. For the bromination of aromatic substrate in aqueous medium, even people are using now liquid bromine. If they don't want to recover that 50% HBr, still they can, because bromine in water, you will get HBr and BROH. But that is not economic. And liquid bromine again, handling, transportation, utilization, it poses a lot of difficulties. So there are many reasons, but HOPR to generate selectively BROH species, so I don't think any other reasons are available. Only if you maintain any bromide salts in this ratio, selectively you can generate BROH that we have proved through the UV visible spectroscopy. So that generates only BROH species, you can see that. No other species are there. But you have to maintain this ratio, and the pH is approximately 4 acidity. The aqueous solution will be pH will be 4. If it goes below 4, around 2 and 1, again this BROH disproportionate, that's what I told. You have to maintain around 4 pH aqueous solution, so that you will get selectively BROH. So maybe you can use this as a solid for transportation easy. So yeah, there are other reagents, but they are all not economically viable, as I told. For large scale manufacture of industrial application, this is the only the source where you can use. And also this is a very cheaper, even compared to liquid bromine, it is very cheaper because it is intermediate. Before converting liquid bromine, it is used as intermediate. Always intermediates are very cheaper than the final product. Yes, yes.
Yeah. I think in your list of brominating reagents, you can leave it, there is one reagent missing. And this is bromide anion, and this is bromide anion in combination with hydrogen peroxide using bromo-peroxidases. And I'm sure that in your department you are working also with the halo-peroxidases like the bromo-peroxidases. I'm pretty sure that your department is active in that field. Can you compare the method with your method? And I mean, I would say if you just need bromide anion, that should be even better.
As I told, so there are hundreds of reagents. I did not indicate that what you are told, but you can use, there are variety of reagents where for industrial applications there is none of the reagents are cheaper than this intermediate. None, economically, because this is actually the intermediate. Before recovery of bromine, we are obtained as intermediate. So you will not get the cheaper material than this.
You don't know this. You don't know this.
Yeah,
now there are so many enzymatic processes in industry. So I mean, your department probably works in this field, right? So do we work on haloperoxidase in your institute?
Hydroperoxidase I did not work.
Yeah.
So when the industrial means collation of industry, once you have the process, so you have to survey what are the available cheap available sources to transfer the technology.
Yeah, it will be
but,
cheaper.
Yeah.
Anybody, it will be cheaper. You
Enzymatic.
need only bromide. You need only bromide.
Bromide is not cheaper. If you take sodium bromide, pure
No,
NaBr.
you took the bromide from your
Intermediate.
from a solvent.
Yes.
You have solvent, right?
Yeah.
This is, you call it bitter.
Bitter.
And this contains magnesium bromide.
Yes.
Yeah?
Also,
So you simply, this is my question.
Yeah.
You simply, can you use this bitter and just do enzyme catalyzed reactions with that? That should be possible.
No.
Why?
Because bitter, it contains most of the salts like magnesium bromide, calcium chloride, sodium chloride. In addition to that, there are other carbonates. It's a bitter, it's a sea, mineral sources. There are a variety of sources are available from the sea, natural source. Selectively, you cannot get the bromide. So,
but okay, you can play around with the oxidation redox potentials of the peroxidases. I mean, it would be worth to try this, because then you could use your bitter directly. I don't know this, but
any enzymatic or any catalytic reaction does not work under aqueous conditions, first of all.
Yes,
because
we work under aqueous conditions. Yeah.
with enzymatic.
Yeah, and also in mixtures of aqueous and organic solvents. What is your
Maybe
problem?
it may work, but selectively, how do you get the bromide?
Huh?
Selective bromide source, like NaBr, calcium bromide.
So it's very simple. There are chloroperoxidases which have a redox potential which is able to activate chloride into chlorine, and also there are bromoperoxidases which I don't know how selectively, but which may selectively transform or oxidize the
It
bromide
may.
into
So that is maybe redox reactions it may work, but again the cost will come. Compared to this process, economically I don't think that is viable for large scale applications.
This is what you never know before, since I think this is no argument.
Yeah.
Because you don't know the economics and I don't know the economics,
See,
right?
whatever the bromide species currently in market available, commercially you take any reagent. So it is not cheaper than this intermediate. That is one. But enzymatic also, that enzymatic process is only selectivity may be there. But if you go to large scale industrial applications, I don't think it is viable.
Of course it is. I mean, my question was, do some people in your institute work on this?
Peroxidase, no.
No, okay, right.
No.
I see.
So we just compare the all existing reagents for bromination
I
process.
understand this.
So no other reagents are cheaper than this process.
Yeah, I understand.
The substrate that we have used is mainly having electron donating group. In presence of electron withdrawing group, for example, the presence of carboxylic acid or any other, can we do the similar type of domination?
Only one withdrawing group in aromatic system, it does not work. If you take nitrobenzene, it does not work. Even benzene itself, as I told, it is a neutral substrate, it requires some heating. We tried with, if you use only benzaldehyde, you will get the first oxidation and then substitution. But as such, nitrobenzene, electron withdrawing substrates will not work. For substitution, for oxidation, it works. Even nitrobenzyl alcohols, I have shown the example. Only for aromatic substitution, the presence of electron withdrawing groups, it does not work. Without withdrawal.
Thank you.
Just another question. You presented this very interesting conversion of the citronellol into the rose oxide.
Rose oxide, yes.
Can we go to your slide, please? That was very interesting. Very nice.
That is with the iron or derivative.
Yeah, here it is. So, my question is about the stereochemistry of your process.
Yeah.
Can you please be so kind and comment on that?
Yes. So stereochemistry we did not observe, we did not measure. It may be mixture because we are starting with this isomer is also a mixture.
Okay, so you
It will end up, final product also will end up with a mixture.
right, okay.
We
right.
did not even think of that stereochemistry.
So you did not deal with the enantiomer selectivity. So you started with racemic or a mixture of
We use a racemic, maybe we end up with a racemic.
Right.
We did
okay.
not,
So,
stereochemistry we did not at all.
Also you did not study the diastereoselectivity.
No, because
Okay.
again that whatever is the, it will undergo elimination of,
Okay.
we did not go into the stereochemistry.
Was just a question. Yeah, thank you very much.
So in case of aniline bromination,
Aniline bromination. Yeah.
so we end up with para-bromination.
In aniline bromination, so we are end up with para-bromination.
This one you are talking?
Yes.
Huh? No, whether this one or others.
Yeah, this one only.
Uh-huh.
What
Only
we are using para-brom.
Para-bromine you will get. But here we are not using our green brominating reagent. This is a reagent. This we can prepare with our reagent. If you use this as a reagent for the selective monobromination of aniline, this is not our reagent. Here we are using our reagent. We prepared this tetrabromocyclohexadienone, which is a good reagent, selective reagent for only for monobromination of anilines, aromatic anilines particularly. So you will get selective para-bromo, and this is again if you add simply alkali, so aqueous alkali, it is a water soluble. So you can again take that salt, add it out. This is in liquid form. Water, it is not, bromine is not soluble in water. So this is soluble in water because it forms the sodium salt. It comes into aqueous, and again take that aqueous, add our reagent, reconvert back to this reagent. You can again separate this, use this reagent for monobromination.
Thank you, sir.
So our reagent indirectly plays role to prepare starting from phenol to this tetrabromo, or if you get tribromo, use one equivalent our reagent, you will get tetrabromo. That is it.
Okay, sir. And one more question. In heterocyclic bromination, like in thiopane, you used DCM as a solvent, and in pyridine bromination, you used ester-neutral as a solvent. So you use different types of solvents there.
Finally, see, when you screen different solvent, different conditions, then only optimized conditions, only we go for the bromination of or other substrates. First we have to screen, so then we can go. Ester-neutral is a very good solvent for some types, and dichloromethane is very good solvent for benzylic brominations, and only sometimes bromohydrins we use aqueous dioxide for bromohydrins. So before extending the substrate scope, first we screen with, see, solvent plays very important role in forms of various parameters. Those are all we didn't study. So based on the best yield, so we go for the optimal condition.
One more question, sir. Since bromine is a very carcinogenic, highly carcinogenic agent, so hazardous and carcinogenic agent. So your green bromine also is like that. I mean,
No.
So have you taken any extra precautions?
No. As I told, it is you cannot see liquid bromine vapors at all. You can conduct the reaction here. I showed the salt. It is like sodium chloride. If it is solid form, dissolve in water, add acid in situ. If you use 2:1 bromide and add acid, in situ it generates BROH species, hypobromous acid. So that is a very good reagent for substitution. You don't see any bromine vapors or color. It is not. That is the reason it is a safe, eco-friendly reagent.
Okay, sir. Thank you.
I have another question. You presented so many nice brominations, and you also reported on the selectivity, the retroselectivity, etc. So, using your reagent, did you observe different outcomes than with traditional brominating reagents, or is it more, or does it more or less give the same product distribution?
Particularly, your question is very valid. When this journal is submitted for industrial engineering chemistry research, so we have clearly, if you go through that comparison, we have given one table using liquid bromine, KBr sulfuric acid, N-bromosuccinimide with the geolite process. We have given because I did not mention here. So there is separate table we have given. So the same questions reviewer asked. I don't know, you may be the reviewer also.
No.
So we have performed and given the separate table for the comparison.
Yeah.
So yes, it is a valid question. So we have done it and given separate table. It does not work. Yeah, please.
Bromination process, which solvents are used?
Can you just use it a bit louder?
In organo brominations, you are saying that solvent used, but can we use any solvent?
Solvent.
Solvent, yeah.
You can use any solvent, depends upon, see, it is the water is essential. Unless otherwise you take water, bromide salts will not dissolve in organic solvents. You need to dissolve this bromide salts in water. That you can take either dichloromethane, ethyl acetate, any organic solvent. For phenols, we don't require any organic solvent. For phenols, that I have shown one bromoxynil that we have performed only in water. You will get, because phenol is at 70 degree, it is water soluble. And after the bromination, that product is insoluble in water. Easily you can separate out. For other reactions, as I told, sometimes it requires acetonitrile, sometimes it requires dichloromethane for chlorination, benzylic halogenation. So organic solvent, you have to choose what type of substrate you want to brominate, so that you can use according to that solvent.
You had BRS as well as BRA. What exactly the difference between those two?
Oh, but actually BRS will generate BROH and BRA will generate BR2, elemental bromine. Is it here? Somewhere I have given. Yeah. See, BRA means 5:1 ratio as an intermediate itself if we add. Sorry. Yes. So this intermediate if we add acid, there is a lot of difference. If you add 6 moles of acid with respect to this bromide, you will get Br2 in situ. So that you cannot see even color of bromine. It will add across this double bond. You will get dibromo. That is called BRA. Whereas BRS is a 2:1 bromide bromine, and if you add 3 equivalent, all are half of this. So you can just generate this BROS, and if you add olefin or this also, you will get the bromohydride. So BRS means 2:1 bromide bromate, and BRA means 5:1 bromide bromate and 6 equivalent acid. BRA. Addition reaction, substitution reaction. For addition also you can use this, so you will get the bromohydrates. That is the difference.
So in one of the bromination, you have used 2 equivalents of bromide bromate. So one of the bromination like anisole, give only monobromination. All the other compounds have given dibromo compound. Only anisole give parabromo anisole. Why is it so?
No, it depends upon the substrate which you want.
All the other substrate have given dibromo exclusively only.
Which one? You are talking this anisole?
Not that one, previous one. In one of the slides.
This one?
No, not this one.
No, it is not like that. You have to use one equivalent. If you use, you will get even for the phenol, monobromination of phenol, we obtain parabromo, mono and dibromo, 81:9, I think 19 ratio. In the case of this, one equivalent you will get this ratio para and ortho ratio. Only mono, para ratio, para ortho ratio is this. If you use 3 equivalent of the reagent, single product 93%. If you use 4 equivalent of reagent, this one or this one. So if you use 1 equivalent, you will get this alpha bromo naphthalate. If you use 2 equivalent of this reagent, you will get the dibromo. This depends upon the substrate, what type of, how many bromide atoms you want to substitute in the substrate. Accordingly, you should use. It's not like.
So you are using HBr and H2O2 to generate HOBr. Can I use KBr and H2O2 to generate HOBr as well as KBr and
I think you can. KBr also you can use. KBr and water, H2O2, you can just, maybe acidic medium you have to maintain again. If you use neutral salt.
As you are telling, HBr is not that much affordable compared to bromine. Can we substitute with KBr or NaBr?
That is more costlier than HBr.
KBr is much costlier.
Yes. Any pure salt, you take KBr and NaBr, it is more costlier than simple HBr. EQS HBr is 35% you will get. That is more cheaper compared to pure NaBr KBr. You see the cost of very pure salts, which is very, very costly. So any more questions? I will be here up to tomorrow if you have any questions. So maybe we can discuss, you are welcome. So maybe you can write if you have any doubts also through my mail. Yes, Professor.
Yeah. So if I may suggest one experiment, you obviously you make some advertisement for your procedure to bring it to the classes. You also have described here the preparation of these tetrabromocyclohexadienone, right? Which is a nice thing, right? And when I lecture on aromatic compounds, on phenols, then I always show one experiment, namely the reaction of phenol with bromine. I take bromine.
Yeah.
So you could just
Get selective parabromo.
one could replace this experiment with bromine with your mixture of reagents. And so you could, let's say, I think many people use this for demonstration.
Yeah.
Maybe that this would be a nice method that you could sell in Journal of Chemical Education as a teaching experiment.
Yeah, thank you.
Maybe,
For your
I don't know.
Yeah,
That
it is
would be
possible.
nice.
It is possible. Why I have selectively chosen that? You can, without any column separation, mechanically you can separate it organic and aqueous. aqueous will come into this tribromophenol, whereas bromoaniline will goes in organic. So easily you can separate the aniline and phenol. So whereas in the case of phenols, both will come into aqueous. Again, you need the separation process, either column cryptography. So it definitely it works. So that you can do it. Only for easy separation for industrial mechanical separation, we have showed that aniline bromination with the tetrabrom. Phenol also definitely works. But there are reports also that tetrabromocyclodienone can be used for selective monobromination. Only we have to separate it by chromatography. This is possible. Yeah. Okay. Thank you.
Thank you, sir. Thank you very much. Now I will request Professor U. Beifuss, sir, to hand over a memento to Professor S. Adimurthy, sir.
Yes, sir. Yeah. So, Professor Adimurthy, thank you very much for your very inspiring lecture. That was very nice, showing how valuable, let's say, the resources of Mother Nature can be used for selective reactions. So, thank you very much again. And this is obviously from this area here. I have been told this is a very rare animal and is found only here in the hills. So, good luck with this animal.
Thank you, sir. Thank you very much.
Has a special name.
So, thank you for your kind attention. Now I request audience and our respected dignitaries to have a tea and please come inside. So, apart from we are chemists, we are also like, we like enjoyment everybody. So, we will have some short music break along with your tea. Okay? But don't dissolve your music in tea. Okay? So, please carry on.
popular start with the Glaser coupling, and the Glaser coupling is nothing else but the homocoupling of alkynes, and you start with two acetylenes, and in the presence of catalytic amounts of copper chloride in aqueous ammonia and ethanol, you get a copper acetylide. This is another aspect of copper. Copper forms bonds with acetylides, so copper acetylides are formed very easily. And here, under these conditions, the copper acetylide precipitates on addition of oxygen or air, again in this mixture of aqueous ammonia ethanol. It dissolves again, and homocoupling just occurs, so that we end up with a homocoupled 1,3-diene. So this original procedure was developed by Glaser as in 1869. So this is a really very old reaction, very old example of organic synthesis. Later, this procedure was modified by Eglinton, and then later by Hay, who used catalytic amounts of copper chloride Schmeder, oxygen as the oxidant, and a solvent. And also here homocoupling could be observed. And here just come the first example of contributions from both India and Germany. So Professor Adimurthy, Professor Malaka, and also I myself, we were involved in improvement of reaction conditions, and here is a typical example given in 2 molecules of acetylene were reacted in the presence of only 2 mole % of copper chloride oxygen. We could use DBU as a base and 1.5 mole % Schmeder. The solvent was acetonitrile, and room temperature in reaction with reactions times vary between 6 and 36 hours. The corresponding dienes were formed with yields up to 99%. So there were certain examples reported. So I want to go further, would like to proceed with the Chodkiewicz-Kallio coupling. And here now we have a heterocoupling of alkenes. We start with one alkene given here, and then add copper chloride, hydroxylamine hydrochloride, diethylamine methanol nitrogen, and when we have done this and have formed the corresponding copper acetylide, then a corresponding bromoacetylene is added, and a heterocoupled product is formed. And this is a reaction that has also been reported a couple of decades ago, but still is in use. Castro-Stevens coupling also deals with the heterocoupling of alkynes. Here, an aryl halide or a vinyl halide is reacted with an acetylene in the presence of a copper-1 complex or a copper-1 salt, in the presence of base solvent, and usually you have to apply reflux, and then you end up with a dye-substituted acetylene. And if you have a look at the substituents that can be used, R1 equals to aryl and vinyl, so the halide is iodine or bromine. And if you have a look at the R2 groups, then alkyl and aryl substituents are usually used. Quite a number of bases can be employed, and the idea is that you first form again the copper acetylide, which then reacts with the corresponding halide, with the alkyl or aryl halide. And currently it is believed that a transition state of this type is formed. Then copper halide is split off, and the dye-substituted alkyne is formed. So this is the Stevens-Castro or Castro-Stevens coupling. Both names are used. And then we come to something what is a bit more modern. So first has been it has been invented in 1975 by Isono Gashira and his colleagues, and this is what is now known, very well known, as the Isono Gashira cross-coupling. And here we have two catalysts. We have a catalytic palladium 0, or we have catalytic amounts of palladium 2 together with the ligand. We also need catalytic amount of a copper 1 salt, a base, and a solvent. And what we can do is, what we can achieve is again cross-coupling products, and they arise from reaction of a halide, a chloride, a bromide, an iodine, also triphlates can be used, and an alkene. And here you can see some of the substituents that can be used for this purpose, some of the palladium catalysts that are used, and when it comes to the copper salts, copper iodide or copper bromine are in use. A number of bases have been used for this process, and also there are a number of solvents that can be used. This is a method that combines palladium catalysis with copper catalysis. So here is a proposed reaction mechanism that researchers came up with. So what does happen? What is the copper catalyst for? Again, the formation of the copper acetylide. So you start with the acetylene, with the alkene, and reacted with a base, and then reaction with copper halide takes place to form this copper acetylene. This copper acetylene undergoes transmetallation with this palladium 2 species, and this palladium 2 species is formed from a palladium 0 species, reacts with R1X under oxidative addition to give this palladium 2 species. Now transmetallation does occur to give this transmetallation intermediate, palladium 2 again, and then finally reductive elimination takes place. And after reductive elimination, you end up with the cross-coupling product on the one hand side, and with the palladium 0 compound on the other hand. So this is the mechanism that is usually accepted for the Isono-Gashira coupling. Very important process. So oxidative phenol coupling, I introduced that topic to you yesterday when I presented some results from our own lab with in the field of enantioselective oxidative phenol coupling. So we used this dirigent proteins and this the dirigent proteins and the enantiocomplementary dirigent proteins. But of course there is also a more chemical solution for this problem. So I do not want to repeat what I have presented to you yesterday. It's the same story that I presented to you. Very often we need stoichiometric amounts of toxic reagents to perform oxidative phenolic couplings, and very often we observe there is a lack of regio and stereoselectivity. So nevertheless, there are a number of methods that have been developed and that make use of copper-catalyzed enantioselective oxidative couplings. And here is 2 naphtholes that has been used as a substrate, or to be more precise, of course, 2 molecules of these 2 naphthol. So these 2 molecules of the substituted naphthols are reacted in the presence of 10 mole % of a copper catalyzed, and oxygen is used as an oxidant, reaction temperature 40 centigrades, 48 hours, and what you come up with is an 85 is a coupling product that is produced in 85% yield and 91% enantiomeric excess. That is very impressive. The catalyst that you need to do to get this result is a 1,5-diaza cis-decaline, and this catalyst, which is has to be used in enantiomerically pure form, has been introduced by Kozlowski. And Kozlowski is known for her work in this field very well. and she has also written a review on use of copper in organic chemistry, and I can recommend this review very much to you. So she has a nice method to produce enantiomerically pure binaphthols, and I just would like to give one example, one application of her method in the field of natural products. So she and her co-workers achieved the total synthesis of nigerone. Nigerone is shown here. You see this is a compound with a chiral axis here, and what she does, she starts here with this phenol type starting material. Again, she uses her copper-based enantiomerically pure catalyst. Oxidant is again oxygen, acetonitrile is the solvent, and she obtains 60% of this bis-isonigerone compound, and the enantiomeric excess was 80%. So this bis-isonigerone compound is not the natural product itself that she had it for. So what has to be done is treatment with base, and this is just a rearrangement of these 4-pyranone unit that is shown here. So we have ring opening and ring closure, and we observe this on both sides. This has been published nearly 10 years ago in Organic Letters 2007. Very impressive chemistry, and if you look for more chemistry of this type, then simply search for Kozlovsky and you will find numbers of applications. He's still very active in this field. So let's come back to history again. All of you should be familiar with the Sandmeyer reaction. What do? You start with an aryl amine treated with sodium nitrate in the presence of an acid, or you also produce this T-butyl nitride. You know that you have to perform these reactions at which temperatures, ladies and gentlemen? Which temperatures? Do you remember?
0 or less than 0.
At 0?
Or less than 0. Less than 0 or equal to
Less than?
0.
No, less than 5 centigrades.
0 to 5.
Less than 5 centigrades. That is what you usually have for. And this has to do with this the stability of this aryl diazonium halide. It is not so stable, usually stable at temperatures under 5 centigrades. And then you add a copper source, a copper 1 salt, and then you end up with the aryl halide or an aryl nitride. Doesn't matter. And of course, nitrogen does evolve. So there are a number of variations. For example, you can use here the corresponding aryl diazonium tetrafluoroborate, and if you simply heat it up, then you end up with the aryl fluoride. If you treat it with sodium nitride in the presence of catalytic amounts of copper 1, then you end up with nitrobenzenes. If you simply take your aryl diazonium halide, treat it with potassium iodide, the corresponding iodides are formed, the aryl iodides are formed. And if you treat the aryl diazonium halide with water and heat it up, then you have a nice access to phenols. So this is very traditional chemistry, but still very important. And it has been invented originally by Sandmeyer, again in the very early days of organic chemistry, namely in 1884. Right. Oops, there it was, yeah. So this is old chemistry, as I told you. Now let us come to nucleophilic reactivity of organocopper reagents. This is chemistry that has been developed starting in the 1960s, 1970s, and it is still of great interest for several reasons, and I will just discuss a number of applications. Here, for example, we have an allyl substituted derivatives, and if you react this allyl type of substrate with an organocopper reagent, which I just call R copper in this case, and nothing to say anything about the structure, then you have here a substitution reaction. You also can react your organocopper reagent with an oxyring, an epoxide. What does happen? Ring opening of the epoxide does happen, and the stereoselectivity can be controlled in a very strict manner. You also can react your organocopper reagent with some sort of R1X, maybe some sort of alkyl or aryl halide, and you end up here with the formation of a carbon-carbon bond. And now I would say this is probably the most well-known and the most important process for organocopper reagent. This is what we call the 1,4 addition or the Michael addition of organocopper reagents to unsaturated carbonyl compounds. And here we have an unsaturated ketone, and this unsaturated ketone exclusively reacts in the 1,4 mode. That means we have selective formation of the 1,4 addition product with concomitant formation of the enolate. What is not given here, but what is true, this enolate can be trapped by another electrophile, and that allows you to introduce a second substituent in this position. Very successful chemistry that has been developed. And of course, let us come back to the acetylenes, to the alkynes. Organocuprates can be used to add to the CC triple bond in the way that these vinyl cuprates are produced, and these vinyl cuprates can be used for further modification. So quite a bunch of chemistry of this type. So let me just introduce these organocopper reagents a bit. Here we have different types of organocuprates, and they are named after their inventors, some of them at least. Here we have the so-called Normand cuprates, and these Normand cuprates, they actually are formed by using the Grignard reagent. So this is probably the oldest variation that is available. Then we have R2 copper lithium reagents. These are the so-called Gilman cuprates. And then we have, if you have a look at this, there is one big disadvantage with the Gilman cuprates. We have two substituents that are present in the Gilman cuprate, but only one of these groups R is transferred onto the substrate. That means we spoil one substituent. And so there are some solutions. One solution is called dummy ligands. That means one of the ligands that you use is one of the substituents that you use is a very unreactive substituent that is not transformed. This is one solution, but there are other solutions that can be seen here. One solution are the so-called Knoppel cuprates, which make use of this reagent which is shown here. And it's also possible to use the monoalkyl cuprates, R copper. And probably one of the last additions are the cyanocuprates, and their structure, their formula is given here. So these are the different types of organocuprates. Sometimes they are a bit difficult to synthesize. Most of them are, or many of them are not extremely stable. That depends a bit on the type of organocuprates. But all in all, these are very nice approaches to produce organocuprates that can be used for the reactions that I've presented before. Now let us come to the so-called Ullmann reaction. The Ullmann reaction is also a very old reaction, has been reported in 1901 first. And what Ullmann and his co-worker did was just to react two aryl compounds, and these were usually some aryl halides. X equals to iodine, bromine, chlorine, also SCN is possible. And if two of these molecules are reacted in the presence of copper powders at very high temperature, you end up with a biaryl. And these were symmetrical biaryl in the first experiments. And here your byproduct is a copper, two copper, 1 salts. You also can use unsymmetrical biaryls, as is shown here, and it has been shown that this can be performed in the presence of 1 to 5 equivalents of copper, or the presence of copper 1 salts, and then the reaction is done in the presence of a solvent, and heat is applied, or sonication is applied, and then you can get here unsymmetrical biaryls. However, it is difficult to, and you have to make a very careful choice regarding the substituents here on your starting materials to end up exclusively with unsymmetrical biaryls. So this is simply the history. Number of reaction mechanisms have been proposed. There's a reaction mechanism which involves aryl radicals, which are shown here, and there's also a mechanism that involves aryl copper intermediates. And here the aryl copper intermediate that is formed is this one here. It reacts then with the second, with another molecule of an aryl halide to form finally the biaryl compound. So this brings me now close to the topics that I would like to present to you here at central position. These are Ullmann type condensations. And let me start with the first paper of Ullmann in this area. What he was able to show is that an aniline can be reacted with an aryl halide. He used stoichiometric amounts of copper and he heated up the reaction mixture, but nevertheless he came up with the formation of a new nitrogen-carbon bond. So here we have the product, the diaryl amine. And indeed, if we have a closer look at this reaction, he needs some activation that comes from this carboxyl group, but nevertheless he was able to achieve this. And of course, we have to recognize that stoichiometric amounts of copper are necessary, high reaction temperatures were necessary at that time. But only 3 years later, Goldberg was the assistant of Ullmann, and she was a lady, and Irma Goldberg was able to show that the load of copper could be reduced dramatically. She was able to perform these reactions in the presence of catalytic amounts of copper, in the presence of a base, in a high boiling solvent, nitrobenzene. 210 centigrade boiling point, and within 3 hours the reaction between these antranilic acid and the bromobenzene gave the diaryl amine. And this is now known as the Ullmann-Goldberg amination. Even better, she could replace the aryl amine with this carboxamide. And she was able to show that amides can be used for this type of condensation reaction. Now this amide was reacted with the bromobenzene, again in the presence of catalytic amounts of copper. Sodium acetate is a base, nitrobenzene is a solvent at high temperatures, and you come up with these amide, with this aryl amide. This is what is still today is known as the Goldberg amidation. Right, but not only carbon-nitrogen bonds can be formed, these people were also able to show that carbon-oxygen bonds can be formed. And this is the so-called Ullmann ether synthesis. Here we start with a phenol. It is reacted with bromobenzene in the presence of catalytic amounts of copper iodide. So, however, I have to say here, potassium metal was used to bring about this reaction. So very harsh reaction conditions. At that time, 210 centigrades again, 2 to 2.5 hours, but nevertheless, 90% of the diaryl ether were produced. So that is a method that is obviously valuable, but it needs to be adjusted to modern purposes. And so reaction conditions need to be improved. And then finally, I would like to present to you the so-called Hertley reaction. And the Hertley reaction allows us to form a carbon-carbon bond using Ullmann-type condensation chemistry. Here, a malonic ester is reacted with a aryl bromide. Again, this aryl bromide is activated by this carboxylic function. And now in the presence of 6 to 20 mole % of copper acetate, or in the presence of a copper bronze, in the presence of two equivalents of sodium, in ethanol under heating, this CC formation is formed. And this is what is traditionally known as the Hertley reaction. So if we just sum up, there are some disadvantages of the classical Ullmann-type condensations. Yes, harsh reaction conditions, that means we need strong bases. Sometimes we need stoichiometric amounts of the copper reagents, and high reaction temperatures are necessary. So there are some solutions, and these solutions have paved the way for the highly attractiveness of this methodology nowadays. So we can work using substrate modifications, we can employ the also effect, but as I have pointed out to you, this is not a very new invention. This has already been used in the early days. But what is new is the introduction of copper-chelating ligands, and the big advantage of using copper-chelating ligands is that no use of preformed catalysts is necessary. If you, for example, compare the copper-type chemistry with the palladium-type chemistry, then you will realize that many of the fantastic palladium-catalyzed CC bond formation or CX bond formation rely on using of defined palladium complexes and using defined phosphine reagents. So this is a big advantage in copper chemistry. We do not need to use preformed catalysts. And using these approaches, now the copper-catalyzed cross-coupling reactions allow us to highly efficient build up CN, CO, carbon-sulfur, carbon-phosphorus, and carbon-carbon bonds. And so this is the reason why these CX and C cross-couplings reactions catalyzed by copper are so attractive. Let me give an example for that what I have discussed. So let us come again to the Hertley reaction. So this is nothing else but the Hertley reaction. In 2002, Buchwald and his colleague reported the reaction between iodobenzene and diethyl malonate, two equivalents of diethyl malonate. And Buchwald performed this, and they performed this reaction in the presence of 5 mole % of copper iodide and the presence of 10 mole % of a ligand. And the structure of the ligand is shown here. So this is some hydroxy biphenyl type of ligand. They use cesium carbonate as a base, 1.5 equivalent, and tetrahydrofuran as the solvent. Reaction temperature was 70 centigrades and the reaction time amounted to 24 hours. And after that, 91% of these coupling products could be isolated. So the authors also tried to replace the aryl iodide with the aryl bromide, with the bromobenzene. However, they state that aryl bromides are essentially unreactive under these conditions. So they were not able to react aryl bromides using their process, which is given here. A couple of years later, 2007, Huang and his colleagues reported a solution for this problem. They again used 5 mole% of copper iodide. They used a bit more of the base, namely 3 equivalents of cesium carbonate. Again, they used an ethereal solvent, now it is dioxane. But they replaced the original ligand introduced by Buchwald and colleagues by picolinic acid. And the structure of picolinic acid is given here, and it is obvious that copper can be chelated by the functional groups of the picolinic acid. So this makes sure that chelation occurs very efficiently. So, and then reaction conditions now again 70 centigrades, but now within 2 hours 93% of the CC coupling product are formed. And even better, we can also perform this reaction at room temperature. Now, however, reaction time is much longer, 20 hours are necessary, yield is more or less the same. And you can reduce the load of the copper iodide to 1 mole%. If you do so, then you need to react, then you need to perform these reactions at 70 centigrades for 20 hours. And again, a very high yield of the CC coupling product is observed, namely 90%. Obviously, it very much depends on the right choice of the ligand, or some people also call it the additive. So, and what is even better, Huang and his colleagues were able to show that bromobenzene and aryl bromides in general can be employed in these processes. Here we have a bit more of the copper iodide, namely 10 mole%, 20 mole% of the picolinic acid. They also increase the amount of picolinic acid, 3 equivalents of cesium carbonate, dioxane, reflux, now 32-hour reaction time, but nevertheless we come up with a 79% yield of the CC coupling process. And this example shows you that now copper-catalyzed reactions or of the Ullmann type can be performed under much milder reaction conditions. And I think this is a very illustrative example, has been reported in Organic Letters 2007. Right, proposed mechanism for the Ullmann condensations. There are a number of mechanisms. The most accepted mechanism is the copper-1, copper-3 oxidative addition reductive elimination pathway. There are some other reaction mechanisms which are given here, but which I don't want to go into detail. I just want to show you a very simple proposal for a reaction mechanism, and it starts here with the copper-1 salt, and the copper-1 salt then reacts here with the methylated nucleophile or with the nucleophile in the presence of a base. So then transmetallation occurs and you have this copper-1 intermediate, and then the aryl halide comes into play and oxidative addition takes place to produce these copper-3 intermediate. And then reductive elimination is proposed to finally produce the product of this reaction. So this is one possibility, that namely that the transmetallation is the first step and the oxidative addition is the second step. However, even today it is not clear whether this is the right, whether this is the way the reaction takes place. It's also possible that the order is quite reversed, namely that the reaction starts with the oxidative addition and is then followed by transmetallation. However, even if the reaction mechanism is still under debate, the attractivity of these copper-catalyzed Ullmann type cross-couplings is very high. So here are some reviews on copper-catalyzed cross-coupling reactions, and you see that all of these, or most of these reviews have been come out after 2010, and this documents the popularity of the field. And now there is even a book on this topic, namely the book from Ivano and Blanchard, entitled Copper-Mediated Cross-Coupling Reactions. And here are a couple of wonderful reviews. The only review that is older than 2010 is a review by Monnier and Telefer, and I just mentioned this because this is a seminal review that you definitely should, not only print out but also study. Very interesting review that they have provided with. And here are some reviews on Ullmann type couplings for the synthesis of heterocycles. And even here is a book available that deals with this topic. I have to say, it does not only deal with the topic of copper-catalyzed formation of heterocycles, also palladium-catalyzed synthesis of heterocycle is covered. Nevertheless, very interesting. Unfortunately, a very expensive book. Much more cheaper are the review articles that are shown here, and they give you a very good overview on what is going on in copper-catalyzed or in Ullmann-type couplings for the synthesis of heterocycles. Right, now it's time to switch from the more educational part of the lecture to the part of the lecture that covers the chemistry that we have performed in our laboratory. And when it does come to the synthesis of heterocycles, then one should realize that you need bisfunctionalized substrates. And you see these double functionalized arenes are covered in this book, and this book deals with the synthesis of heterocycles. So you need double functionalized arenes or substrates. And there are different types of bis electrophiles that can be used as substrates for copper-catalyzed domino reactions. And here are just three types. So there is the ortho-dihalobenzene, and this allows for two arylations, for example, for two arylations in a row. And if you are able to distinguish between the two X groups, for example, by making this X to bromine and making this X to iodine, then a differentiation between the two positions will be possible. Here we have the ortho-haloalkanyl aryl halides. They allow arylation here and vinylation at this position. And then we have another group, namely the ortho-halobenzyl halides, and they allow for alylation at this position and arylation at that position. So there is a broad number of substrates, of doubly functionalized substrates that can be used for the synthesis of heterocycles. Let us start with an example using an ortho-dihalobenzene. So here we have this bromoiodobenzene, and this is now reacted with some 1,3-dicarbonyl compound in the presence of 10 mole % copper iodide. Here we also use pivalic, not picolinic acid, but we use pivalic acid, and in the presence of 1.5 equivalent of cesium carbonate, using dimethyl sulfoxide as a solvent, so a dipolar or apolar protic, a dipolar aprotic solvent, and we perform the reaction in a sealed tube at 130 centigrades, and then we come up with this benzofurane type of compounds. Here in total we have published 15 examples, and here are just some of them. And they show you that the yields are usually not that low. Usually we are in the range between 60 and 80%. So you can use acyclic 1,3-dicarbonyls. Here, for example, the pentane dione has been used, And you can also use cyclic 1,3-dicarbonyls here, for example, cyclohexane 1,3-dione has been used as the substrate. This has been published in 2012, and the major contributor was Nayev Al-Jan, and this is now chemistry here again from our laboratory. So there are a number of biological active compounds with a 4H1-benzopyrene moiety, and this 1-benzopyrene moiety is shown here. A couple of molecules. Here again we have this moiety. This is a compound with anti-cancer properties. This rhodomertin is a natural product exhibiting antibiotic properties, and this myrtocomulone E is an alpha-glucosidase inhibitor. So it seems that these type of compounds show some promising biological activity, and this is why we decided to embark on a copper-based approach to this sort of skeleton. So the idea was very simple now to start with an halobenzyl halide and react it with a 1,3-dicarbonyl. What we were heading for is this 4H1-benzopyrene, and the argument was, let us start with a C-benzylation here to form this intermediate, and then in the second step an O-arylation might take place between the enol that is formed from this ketone, for example, and you would end up with the 4H1-benzopyrene. However, there might be a competition reaction. You could start with the O-benzylation instead of the C-benzylation. This would give rise to this sort of intermediate, and this intermediate here could undergo a C-arylation. And if it does undergo a C-arylation, then we would end up with these 1H2-benzopyrene. So the question was, would we get mixtures of the two compounds, or would we get selective formation of one of the two possible products? So we came up first with we did the reactions, and when we reacted this halobenzyl halide, it was this bromobenzyl bromide with beta ketoesters in the presence of 20 more % of copper iodide, in the presence of 4 equivalents of a base, potassium phosphate, DMA, again reaction in a sealed tube, 110 centigrade, 24 hours. Then indeed the 4H1-benzopyrenes are formed selectively. So everything starts obviously with the C-benzylation as given here, and then the enol or the corresponding enolate do undergo an O-arylation to form the final product here. And this is now chemistry that has been performed by Professor Malaka, and it has been reported, has been published in Organic Letters in 2011. So obviously a selective reaction that takes place. Of course, we tried to transform or to make use of this chemistry and replace the beta ketoesters with 1,3-diketones. For example, this cyclohexane diol. And again, under very similar reaction conditions, 20 more % copper iodide, 4 equivalent cesium carbonate, DMF, sealed tube, and no ligand added, no ligand necessary. We came up not with a single product, but unfortunately with a 1-to-1 mixture of 2 products. And this is the expected product that arises from C-benzylation or arylation, and this is the product that arises from O-arylation. The second step, the C-arylation does not take place, so we end up with the O-benzylation product. So obviously this is no proper solution to get high yields of these tetrahydro 1H xanthine 1-ones. What we did is, we killed, so to say, the domino process, and we made it in 2 steps. We first did react the bromobenzyl bromine with the 1,3-diketone under basic conditions, and we exclusively observed the formation of the C-benzylated compound. Then we take the C-benzylated compound and we react it under the influence of catalytic amounts of copper chloride, base, phthalic acid, DMF, as I've already shown to you, to convert this into the required heterocyclic product. So here exclusively O-arylation takes place, and I would like to point out that we only require a tiny amount of copper chloride, namely 0.5 mole %. So here we have established this chemistry in 13 examples. Yields are very high, somewhere between 83 and 99%. Now this brings me again to the chemistry that has been performed by Professor Malak now earlier on, and again we have here the bromobenzyl bromide, but now we reacted with an excess of the beta-keto esters, and then something different occurs. We do not observe the formation of the 4H1 benzyl pyrenes, but now we come up with the formation of naphthalines. And what you can observe here is that 1, 2, 3 bonds are formed in one go. So here we have, now I would say, more or less typical reaction conditions: 10% copper iodide, high load of 2-picolinic acid as a ligand, 4 equivalent of cesium carbonate, and methylpyrrolidine as the solvent, sealed tube, 100 centigrades, 24 hours, and this gives 65 to 80% of the corresponding naphthalines. Here are some products that have been synthesized, and as you can see, we can play around with substituents on the starting material, but in all cases, and you also can see that you can play around with the structure of the beta-keto esters as shown here. So this is a reliable and highly selective process to come up with these at least three substituted or even higher substituted naphthalines. So a possible reaction mechanism starts with the C-benzylation, which is given here and which I have shown you before. And then instead of an O-arylation, the reaction of this aryl bromide with a second molecule of beta-keto ester takes place. So here C-arylation is the next step of the proposed reaction mechanism. After the C-arylation, deprotonation at this position takes place, and a 1,2 addition onto this CO double bond occurs. This forms now this bond. This is now the third bond that is formed. Obviously, this is not the end of the whole story. Here we produce an O-, an alcoholate, and this alcoholate probably undergoes 1,2 attack to the CO double bond, and some sort of oxetane is formed, which is obviously under high strain and which decomposes with liberation of this carboxylate and with liberation of the product that we want to have. The only thing that remains to be done is aromatization at this position, and this aromatization obviously occurs under reaction conditions. So this looked quite nice, and so we came up with some functional group variation. So now we did not react the bromobenzyl bromide, but here we used just the C benzylated starting material. And we reacted it with a beta-keto ester, and when we do so, then the ester functionality is retained in the target molecule. If we react this starting material with a malonate, then of course one of the carboxylic ester groups are retained, and if we react them with cyanoacetic esters, then the cyano group is retained. And that means there is definitely some selectivity in this process, which of the group does remain in the molecule and which of the group is liberated. So another application of this sort of chemistry is the copper-catalyzed synthesis of quinazolines in one pot. And the special thing about this method is that the reaction can be performed in water under aqueous conditions. Again, we start with the bromobenzyl bromide, and now we react it with an amidine, or to be more precise, with an amidine hydrochloric, with the salt, with the hydrochloric salt of an amidine. Reaction conditions: 10 mol% copper oxide, 20% dimeda, 4 equivalents of the base, and here water is the corresponding solvent that has been used. And as I've shown you now several times, we make use of sealed tubes, and the reaction temperature was 100 centigrades, and we end up with yields somewhere between 57 and 85% of these substituted quinazoline. So reaction mechanism: probably we start with the nucleophilic substitution to give this intermediate, which is then followed by intramolecular anarylation to give this intermediate. This intermediate then needs to aromatize, which is shown, which it does under reaction conditions. However, we cannot exclude that the reaction occurs in the reverse order, namely that we start with the anarylation to give this sort of intermediate, and then is followed by an intramolecular substitution reaction, again to give this non-aromatized intermediate. So this was published a couple of years ago, Chemistry European Journal. So there is nothing bad about the bromobenzyl bromides. But when you work with benzyl bromides, or when you work with benzyl chlorides, who of you did work with benzyl chloride? Did any of you work with benzyl chloride? So these compounds can be used as tear gas. Right, and this is the problem. A little bit high vapor pressure, and this is why it might be a good idea to replace the bromo substituents with another reactive functional group. And we decided that we wanted to replace the 2 halobenzyl halides with 2 halobenzyl tosylates as their substrates. They don't have these ugly properties. And we wanted to show that copper-catalyzed synthesis cross-couplings can be performed using these 2 halobenzyl tosylates, and we decided to use these 2 mercaptoimidazoles as substrates. And as you can realize, these 2 mercaptoimidazoles, they also have 2 reactive centers, namely the SH group, the mercapto group, and also here the NH group. So S nucleophile and an N nucleophile. And here we have 2 C nucleophiles. So indeed, what we find is the product formation, and as you can see here, everything starts with the S-benzylation and is then followed by an intramolecular N-arylation. Here are some of the compounds that we obtain that are imido-azo-benzothioanes. And the selectivity of this process is very high. We always observe the first step, the formation of a CS bond. Another thing that we have studied recently is a new dimerization process, but now it is probably a dimerization process that makes not use of phenol coupling or of radical couplings. It is probably a pure anionic dimerization process. So we have here these sort of aryl substituted beta ketoesters, and they are reacted under, I would say now, typical reaction conditions that I have presented to you. And what we come up with are these highly substituted naphthalenes. And if you analyze the product structure, then you will realize that here two bonds have been formed during these reactions. Here are some selected products that we have synthesized. Yields are in most cases good to very good. However, there are some examples where the yields are much lower. So this work has been performed by Heike Reichschädel and has been published recently. So with respect to the reaction mechanism, we believe that the reaction might start with a condensation between this carbon atom here and the CO double bond to form this CC double bond. And then everything is placed for an intramolecular C-arylation, namely between this carbon atom and this carbon atom here. The only thing that is missing is isomerization, and the isomerized product is the final naphthalene type of compound. However, again, we cannot exclude that the reaction takes place in reverse order, namely that it starts with the intermolecular C-arylation followed by condensation. Now, another piece of work that I would like to introduce to you is a double intramolecular Ullmann coupling, and this has been performed by Hans-Georg Imrich, and it has been published in 2015 in the European Journal of Organic Chemistry. So we wanted to show that heterocycles can also be built up by using double intramolecular Ullmann coupling. And what we did is we synthesized these 1,2 diols, and these 1,2 diols are connected to an aryl halide type of substituents. So these are Zyn 1,2 bis 2-haloaryl ethane 1,2 diols. And these compounds can be obtained in diastereoselective manner. They also can be obtained in enantioselectively pure form by using the sharpless methodology. Now, when we have these after having synthesized these starting materials, then we perform a reaction with 10 mole % of copper-2 oxynate in the presence of 1 equivalent of potassium iodide, 4 equivalents of potassium phosphate as the base. We have a mixture of acetonitrile and water as the solvent, and reaction is performed at 100 centigrades, and reaction time is quite long, takes 3 days. What is remarkable is that we here start with a copper-2 reagent. However, and this is a copper complex. Do you know what a copper-2 oxynate is? Obviously some sort of ligand. Copper-2 oxynate. Anybody has an idea what a copper-2 oxynate is? So this is nothing else but the complex of copper-2 and 8-hydroxyquinoline. 8-hydroxyquinoline. And this is called the copper-2 oxynate. Right. And what you see here is that we start with a copper 2 oxynate, but that we make sure that a reductant, namely potassium iodide, is present. And the job of this reductant potassium iodide is to reduce the copper 2 to copper 1 during reaction. I don't have any idea why this works better than using a mixture of copper 1 salt and 8-hydroxyquinoline, but it does give better results. So here now, this arylation takes place, so we form obviously one bond here, one bond there, and we come up with these dihydrobenzofurol 3,2B benzofurane systems. Here a couple of examples are given, yields are high, and as I told you, you can obtain the compound in racemic as well as in enantiomerically pure form. This has been published 2015 again. Now it's time to switch to other bis electrophiles. So far we have mainly discussed electrophiles with aryl halide bonds. Now let us come to compounds which are vinylic type of substrates. And again, here are different types, classes of compounds that can be mentioned. We have here the 1,2-dihaloalkenes with 2 vinyl X bonds. We have here the 1,4-dihalo-1,3-dialkenes, again with 2 vinyl X bonds, and the geminal dihaloalkenes. Here we have also 2 vinyl X bonds. Then there are 2 classes of reagents which have 1 vinyl X bond and 1 allyl X bond. These are the 2,3-dihalo-1 propenes, and these are the 1,3-dihalo-1 propenes. And so far we have mainly focused on using these 2,3-dihalo-1 propenes as substrates, but we are also working on the 1,3-dihalo-1 propenes. Right. What did we want to do? We proposed a route for the copper-1 catalyzed synthesis of furanes using 2,3-dihalo-1 propenes as starting material, and the idea was very simple. Let us use these 2,3-dihalo-1 propene and react it with a 1,3-dicarbonyl, and then what do we expect? An intermolecular C-alidation should be the first reaction and should form this carbon-carbon bond. And then everything is in place for an intramolecular vinylation between this oxygen atom here and this carbon atom here. This should end up with the product of this intramolecular O-vinylation. This is this furan type of compound. The only thing that is missing is isomerization of this exocyclic double bond to the endocyclic double bond, and then the product of this would be this tri-substituted furane. This was the idea, and we started with a model experiment using this 2,3-dibromo-1 protein. We did react it here with several 1,3-dicarbonyl compounds. This reaction could be performed in the presence of 10 mole% of copper iodide, and at that time we performed the reaction or in the presence of 1 equivalent of hydroquinone. And the reason for that was that at that time we believed that the hydroquinone is necessary to prevent polymerization. But meanwhile, we have been able to show that you do not need to employ these 1 equivalent of hydroquinone at all. That is not necessary. But we published this using this procedure here. Reaction conditions, here again, no ligand is necessary, 4 equivalents of cesium carbonate, DMF, and the reaction temperatures that I have presented several times. So we end up with the formation of these tri-substituted furanes here. Here are some of the products we have synthesized. We can play around, obviously, here with the structure of the beta ketoester quite a lot. And it's also possible to play around with the structure of this aryl substituents. So here we have replaced the phenyl group with a fluorophenyl substituent. So this is possible to do variations in these in the different substrates. So the next question was, is it necessary to have an aryl substituents in this position here in the corresponding, this would then be the 1 position in the here. And so this is the reason why we synthesized this alkyl substituted 2,3-dihaloprotein, and we reacted it under reaction conditions that I have presented to you. And obviously it is possible to do so. We ended up with 80% of these alkyl substituted furane. Reaction conditions are not optimized. What is the reason to do so? The reason is that there are some potential targets, and they are the so-called furane fatty acids. What are furane fatty acids? The gross structure of furane fatty acids is given here. They are widely distributed in nature in different types of organisms, in algae, in plants, microorganisms, animals, but their precise roles are uncertain. What is known is that these compounds are highly reactive, that they can be easily oxidized, and that they act as radical scavengers. So antioxidant properties, anti-tumor properties, and anti-thrombotic properties have been demonstrated. However, the real importance of these compounds is not known. But if you read this review of Professor Spitella from 2005, then you will get an idea why people are so much interested in furane fatty acids nowadays. The title of this review was Furane Fatty Acids, Occurrence, Synthesis and Reactions. And now the important question is given here, are furane fatty acids responsible for the cardioprotective effects of a fish diet? And so this gives you an idea why we are now interested in the synthesis of these compounds. This question has not been solved so far, but maybe that these compounds play a very specific biological role. Right, what's about 2,3-dihalopropanes? They can also be used. Now the reaction does not take place in one step. We have first to do the corresponding C-alylation, and then the C-alylated product can be transformed under copper-catalyzed to the corresponding furane type of derivative. However, here we have the exocyclic double bond, and obviously the exocyclic double bond is so stable that it does not undergo isomerization to the fully aromatized furane type of compound. Again, here we put the question, is it possible to replace the 2,3-dihalopropane with the corresponding tosylates? And to do so, we want to synthesize these compounds. Our colleague, Mr. Omar, tried to do the synthesis. And what he did is he reacted this allylic alcohol with paratoluene sulfonyl chloride in the presence of a large amount of base, And then accidentally, he did not produce the compound that he wished to produce, but what he did come up with was this propagaryl tosylate. Okay, but he thought, why not using this propagaryl tosylate as a substrate for a copper-catalyzed transformation? And the idea was that he wanted to synthesize imide thiazoles and also thiazolobenzimidazoles. Their general structure is shown here. And the idea was, let us start with this propagaryl tosylate and let us react it with a 2-mercaptoimidazole or a 2-mercaptobenzimidazole. And in the first step, a S propagation should take place forming this new carbon-sulfur bond. This is what we expected, and then we expected a cyclization, a so-called 5-exo dick cyclization, and this should establish a new bond between this nitrogen atom and this carbon atom here. And then after double bond isomerization of this exocyclic double bond, then the product should be obtained. Obviously, somehow this chemistry worked. This was published in 2014 in the Journal of Organic Chemistry. But to tell you the whole story, when we did the reaction, then first the reaction was done in the presence of 10 mole% copper iodide. The product was obtained. But then, after doing all the experiments, in particular after doing the optimization experiments, in one of the final experiments, which you always should do, namely the control experiment, then he realized the whole thing can be done without copper. And if I may give you some advice, do the control experiment earlier. Since what do you have now to do? Now you have to restart optimization and so on and so on. So on the other hand, you also have to make sure that no copper is available in your reagents. And here we checked whether the cesium carbonate does contain some copper or not. So we checked whether copper is available, whether iron is available, whether nickel is available. What we did not check, I have to say, if we want to ask a question like this, we did not check for palladium. Unfortunately, we didn't. But obviously, the yields and the reaction conditions are more or less identical, so there is no need. So we can do this under transition metal-free conditions. And I have to say, as always, it's very nice to work with transition metal catalysts, but it is even more attractive to avoid them. That means to work under transition metal-free conditions. Right. Okay. Here are just some of the examples. Some are here he reacted. Some of the probabilic tosylates with a number of the 2-mercaptoimidazoles and benzimidazoles. Here reaction conditions. Yeah. Now these were the original reaction conditions. Now he had to optimize again. Now we came up that 2 equivalents of potassium carbonate are fine. Isopropanol, a protic solvent, can be used. CO2, 70 centigrades, 15 hours. 15 examples of these thiazolobenzimidazoles and these imidazothiazoles. And here you just can see that there is some substrate scope in this reaction. And as I told you, that has been published a couple of years ago. This is what we are just doing at the moment. We are just studying the use of 1,3-dihalo-1 proteins. So switching from the 2,3-dihalo-1 proteins as substrate to the 1,3-dihalo-1 proteins. And obviously this reaction can also be performed. Here we have a cyclic compound as substrate. We reacted with this cyclohexane with the cyclohexane 1,3-dione type of compound, namely the dibidone, and in the presence of catalytic amounts of copper iodide using cesium carbonate as base in DMF, 80% of this tricyclic compound are obtained. And obviously here a domino C-alylation takes place in the first step and is followed by an intramolecular O-vinylation. Selected products are given here, and as you can see, you can play around with the ring size. So the 6,6, 6,5, the 8,6, the 6,5, and the 5,6 combination has been realized. And as you can imagine, you can perform a number of experiments. We are just on our way to finish this, and the person who is doing this is Mehran Fumani, who does come from Iran, and he is dealing with this sort of chemistry. Now, I think I should come to an end now, right? I think you don't need any more copper-catalyzed chemistry. Do you want to have one more example, or should we stop here? Be honest. What is the answer? I didn't get the answer. Stop now? You want to work me. You want to make me work me. Yeah. I worked yesterday, and so I should work today. Right. This is another Indian example of chemistry, I have to say. This sort of chemistry was performed by Kavita Sudendran, who came with her husband to Germany and who joined my group. Now both of them live in the US and work they work near the Rocky Mountains in Denver. This is what my last information is, and now Kavita has just started a postdoctoral position in one of the groups of the organic professors there. What she has been able to show is that 3,5-diaryl 1,2,4 triazoles can be synthesized from amidines. Here we have the amidines, or to be more precisely, we have the hydrochloric acid salts of the amidines, and they are reacted with 5 mole% of copper triflate, and in the presence of 3 equivalents of a base, and in the presence of 20 mole% of a phenanthroline, which is a ligand. However, we also need to add 30 mole% of this hexacyanoferrate, and as you know, this hexacyanoferrate is a strong oxidant, and the solvent is also dichlorobenzene. Reaction was performed at 130 centigrades in the presence of air, and reaction time was 24 hours. As you can see, we were not really happy with these reaction conditions, and still we are not happy. I at least am not happy with these reaction conditions for a couple of reasons. 5 mole% copper triflate, this is fine, no problems with this. I also don't have problems with 3 equivalents of sodium hydrogen carbonate, since I know that at least 2 equivalents are necessary to free the base from the hydrochloric acid salt. But I'm not happy with 30 mole% of the hexacyanoferrate. This is an oxidant. And of course we try very hard to avoid this additional oxidant and just to rely on oxygen as the oxidant. But unfortunately this was not possible, and obviously the reaction temperature at the moment is quite high. Of course we are interested to reduce all that. But nevertheless, if you do this reaction, then 2 new carbon-nitrogen bonds are formed in one step. And here are some examples that Kavita came up with, that has been published in 2014 in Tetrahedron. So as I have shown, she was able to use here the amidines, and when we wanted to do here some modification of the aryl group, so just in order to study the scope of the reaction, then we realized that the number of different commercially available aryl amidines is restricted. And so we came up with the idea, is it possible to replace the amidines with imidates? So maybe that you are familiar with imidates and amidines, maybe not. So the idea is that imidates can be synthesized from the corresponding nitrites just by the so-called Pinner reaction. And that means treating with the corresponding alcohol under acidic conditions. And then the imidates can be used as substrates to produce the corresponding amidines by reaction with ammonia. Then replacement of the OR group takes place and the NH2 group is installed instead. And then the question was, can we just use the imidates, 2 imidates plus ammonia as substrates to perform this reaction in order to get the corresponding triazoles? And she was able to demonstrate that this is possible. So 3,5-diaryl-1,2,4 triazoles can be synthesized from imidates just by performing the reaction as given here. Slightly different reaction conditions, slightly higher amount of copper triflate is necessary, but nevertheless that works quite nicely. We also came up with a reaction mechanism, and the idea is that either we start with the amidines or with the imidates. In the first step, there is some sort of a condensation reaction resulting in a nucleophilic substitution, and then these 1,3,5-triazine pentadiene is formed. This is the intermediate C, and then the intermediate C does undergo reaction with the copper reagent to produce these copper-2 complex. This copper-2 complex D just undergo another reaction with intermediate C to produce the complex given here, and then oxidation takes place, either oxygen or the iron 3 salt make sure that an oxidative ring closure takes place, and as you can see, the ring closure is here between the two nitrogen atoms, and this is a nice example for building up an N bond, N single bond by some oxidative ring closure. As I have told you, this was published in Tetrahedron 2014. But I now think we should come to an end. So I have demonstrated some of the results in the field of copper chemistry that we have achieved in our laboratory. I've also gave you an overview on standard copper-catalyzed reactions. So thanks a lot for your kind attention. So if you have any questions, then I can try to answer them. Up to you. On the other hand, we could have a break. So what does our organizer say? Yeah.
So the reaction which were performed in the sealed tubes, so those were the new tubes, or they are performed in the older ones?
Oh,
because
that's
that will be containing the metal contaminations.
Yeah. Okay. Right. This is true. So when we want to make sure that we work under copper-free conditions, then we use new tubes. Definitely, this is true. But when we do reactions under copper-catalyzed conditions, then we don't bother, then we simply use the old ones. Because then it makes no difference. The amount of copper that could be in the glass should be much less than the 5 mole percent or the 10 mole percent that we add, right? So I don't think that this is only relevant when you argue that your reaction is under metal-free conditions.
Right, so you have shown one metal-free reaction.
Yeah.
So in that they have used the new sleeve.
Yeah. Of course, we have done that because we know this is the typical question of any reviewer. How did you make sure that your reaction really does proceed under metal-free conditions, right? So, and I have to say, in the first when we first submitted our paper, then we did not determine the amount of copper and of nickel and of iron by AAS. We simply relied on the information given by Aldrich or the other suppliers of chemicals, and they said 99.9999, and that was enough for me, but it was not enough for the reviewers. He said, no, she or he said, did you make sure? Did you make sure? Okay, then we did make sure that no metal was there in the reaction.
So further discussion you can do later. Okay.
Okay.
So you can have lunch later.
Good.
Good, good, good.
Dr. Mithun sir will going to present his lecture on transition metal, translation of green medicines, green metals into medicines. So please welcome him with big round of applause.
Actually, Dr. Chandicharan Malakar, he started the initiation of just a wonderful thing, that is the GIAN program in NIT Manipur. That will be the excellent opportunity for me to present my lecture on this great occasion. So my topic is that translation of green metals into medicine. So I was very confused about the title, because at the very beginning, then I said, what to give, because I am basically inorganic chemist, and the GIAN course is all about the organic synthesis to the greener horizon. Okay. So I was discussing with Dr. Chandi, so what topic should I discuss? then actually I was doing some anti-cancer activities of some metal-based compounds. So I am mainly using the copper and iron. Okay. So, and in fact these are the green metals, and these metals can be found in the biological system, and they're quite happily they are doing their jobs for various biochemical processes. So it is very important that if I can present those metal ions, if I can present my topic in such a direction, if I take the translation of green metals like iron and copper into the medicines. So now you people must have some ideas that what is the medicinal chemistry, and if you see there's some books of medicinal chemistry, you will find a lot of carbon-based compounds. So these carbon-based compounds that is well marketed, and it is some pharmacokinetics, pharmacological aspects of these organic compounds, they are well studied. Okay. So now what is the basic of this organic-based compounds? So we use it for medicinal purposes. So it is saturated. So carbon, you know, that is sp3 hybridized carbon, that is having tetrahedral geometry, and sp2 hybrid carbon, that is sp2 hybridized, and sp hybridized carbon, that is linear in geometry. So there is a not much flexibility that you can do. So design a new medicine. So only that you can derivatize the compounds, your parent compounds, and to get a lead compound, and then from lead you just do some combinatorial approach and end up with some lot of compounds, and that can be medicinally active. So why is the metal? Why the metal is so important? So it is the medicinal inorganic chemistry that is growing up very recently. You can say systematic exploration was done only after the discovery of the cisplatin. The cisplatin was discovered in 1969 by the Bernard Rosenberg. Okay, and after that, now the scientific community they understand what is the potentiality of this metal ions. So why the metal is special? So you can see the structural properties. So the metals have the ability to organize other molecules, that is the ligands, in a wide range of specific geometry. So that means it can give you a trigonal planar, tetrahedral structure, square planar, trigonal bipyramid, then square pyramidal, then octahedral, and so on. So the geometry of the metal-based compounds that can vary up to 12. The coordination number, it can vary up to 12. So it can take up to 12 or more than that ligands. So that flexibility you have with your metals. Now you can see the reactivity. So metals have versatile reactivity depending on its oxidation states. Okay, geometry and the environment. So reactivity, if you change the coordination pair of the metal or the ligands, then you have end up with different kind of reactivity. So nature, they are very clever. Nature is very clever to utilize this phenomenon of the metal, this aspect of the metal, for various biochemical processes. So let's say hemoglobin. So what is the hemoglobin is having? That is the porphyrin rings, and then there is a histidine, and in between there is an iron. Okay, iron 2 is there, and this space is occupied. This is back end to be occupied for the oxygen to carry. So there are the two oxygen carriers in the mammalian system. One is a hemoglobin, another is a myoglobin. So in the lungs, the oxygen is taken up by the hemoglobin, and then in the low pressure region, that is in the cell saps, where the hemoglobin transfer its oxygen to the myoglobin, and then myoglobin, it carries the oxygen to the cell, and then oxygen is used by the cell for oxidation purpose. Okay. So the thing is that here the metal ion, that is the iron 2 center, and coordinated by the 4 nitrogen of the porphyrins, they are very, very stable, and they are kinetically inert system. So to carry oxygen, it is very, very important that the chemical property of this compound should not be lost. okay, so that it can carry the oxygen to the target site. If it is lost, then you end up with some oxygenated compound, so they cannot carry the oxygen. So it is a very specific activity. Now, just you have porphyrins, now you have changed this histidine into the sulfur. Just slight minor change in that coordination pair, the fifth position that is occupied with this one. And this is also having iron 3 center, and this changes the activities dramatically. So it is the oxygen carrier, and now this is used for oxygenation reactions. Okay, cytochrome P450 is used for oxygenation reactions. So nature, what is the take home message? Take home message is just nature is cleverly optimize the structure in such a way to use the metal ion for different type of activities. So that's what I just mentioned, reactivity. The metals have versatile reactivity depending on its oxidation state. If you have iron 2, it is of no use. If you have iron 3 here, it is of no use. It cannot carry the oxygen if it is iron 3 is there. Then iron 3 inert information is there, and then it is gets deactivated. So it is an iron based record, oxidation states. And this geometry is also very, very important. And the geometry of this coordinated sphere and how the metal environments are there. So if it is some hydrophilic environment there, then your oxygen cannot come, because its oxygen is some of the hydrophobic in nature. So this environment has to make hydrophobic. Okay. So there are some aspects of the metals. And another important is that optical property. So this metal ion, you can see, if you take vanadium ion, plus 2 oxidation state have this color, plus 3 is this color, and plus 4 and plus 5 has different colors. Okay, these optical properties of the metal ion, they can be utilized for various purposes, for diagnostic purpose mainly. Okay, so we'll come to this one very shortly, very shortly. So, and then there's a magnetic properties. Let's say neodymium, iron, and all these metals with the unpaired electrons. So they have the magnetic properties, and these magnetic properties can be used for different purpose. So these aspects of the metal, so it is a very, very important to design a metal based drugs. Okay, so this you require. Now we come to the living system. What is the primary composition of the living system? Now you can see water is a 62% and the protein is a 16%, and the proteins, amino acid, DNA, RNA, all the biomolecules, they primarily contain carbon, hydrogen, oxygen, sulfur, phosphorus. And now you come to this person, this one, less than 1%. So this less than 1%, it contains the trace metal ions. So these are iron, zinc, manganese, copper, iron, cobalt, nickel, and some cases are vanadium, chromium, and then molybdenum are found. So these metal ions present in a very, very trace amount. Trace amount means catalytic amount. So in the previous lectures, you have encountered, so the 10 mole percent, 5 mole percent, even 1 mole percent that is required. So this is a catalytic amount is required to catalyze the whole cycle. So here also these are the biological catalysts. So they are primarily used as a biological catalyst. Okay. So now what is the importance of this metal ion? Okay. So earlier it was not known so much. Okay. So it is serendipitously it was discovered what is the role of metal ion in the biological system. So then it is started the systematic exploration. Okay. So systematic exploration was that, then what is the role? So suppose diet is given to some animals. Okay. You have some rats, that animals, that is guinea pig. Okay. So in that case you supplement, you give a diet that is devoid of some metal ion, and you end up with, the rat is ending up with some diseases. Okay. So then we come to know, okay, since iron is not there, so because of this iron deficiency it has this problem. Okay. Or overload problem. Sometimes you give some excess of iron and you end up with another kind of toxicities. So you can come to a conclusion, okay, because of this presence of excess of iron, so it gives a toxicity. Okay. So like this one, if you can do that one, what is the role of metal ion? So there is a response curve, how the biological system it responds, and then it is the concentration of the elements that is present in the diet. So you can see, so at a very low concentration, a living system, living being cannot survive. Then it is a marginal. So in this concentration range, you will have that living system can survive, but it has some deficiency, so related diseases. And this concentration it is required in ideal condition. So this is the ideal concentration for a living system to have for a healthy life. Okay. And then if you increase more concentration of the metal, you can see it leads to a again toxicity, and then it leads to death. Okay. So excess of things, it is sometimes is very, very harmful. Okay. So after that, it was discovered that what is the role of sodium. So sodium is a +1 charge, and it creates some concentration gradient in the cell membrane, and then creates some potential. And this potential is a very, very important to regulate our cell-to-cell signaling. Then potassium, it is also as a charge carrier and osmotic balance. Then magnesium, these are mainly hold as a structure, hydrolysis and isomerase. So you can see the calcium, then also structure, the trigger, the calcium and they actually trigger in the nerve cells. Then vanadium, then chromium, molybdenum, hydrogen fixation, oxo-transfer reactions, and then tungsten, what is the role of tungsten, and iron you can see, oxidase, oxygen transport and storage, etc. And cobalt is oxidase, okay, then alkyl group transfer. So nickel then is a hydrogenase, copper, they also have similar role like iron, and zinc also has a role of structure and hydrolysis. Okay. So now the nature is using the metal ions in such a way so that they utilize the chemical property of these metal ions, chemical properties of metal ions for specific purpose. Now let's say for example magnesium. Magnesium is a +2 oxidation state in the biological system. Then what is the role, what is the primary property of the magnesium we know? Can you guess anybody? What is the primary property of magnesium? So this is nothing but a Lewis acid property. Okay, this is nothing but a Lewis acid property. So Lewis acid property, it will be very helpful to activate the carbonyl carbon. Okay, and therefore whenever there is a peptidase is involved, let's say hydrolysis of this peptide, so carbonyl oxygen has to be activated. So carbon has to be activated. So you require a magnesium. Okay, for phosphatase activity. So you need to break the phosphate backbone, diphosphate backbone. Okay, phosphodiester backbone. So you require a magnesium in that. Okay. In fact, the ATP, they contain this one, magnesium. Without magnesium, ATP cannot hydrolyze. ATP to ADP plus inorganic phosphate plus energy, that cannot take place without magnesium. Okay. And now, if we can concentrate here, these iron and cobalt and copper. So what is the primary property of these metal ions you have? So, yes. So the primary property of these have, they are transition metals, and they have colors, they have redox property. So these redox properties are very, very important for different oxygenation reactions, etc. Okay. So electron transfer reactions, etc. So it is very, very important to design your system in such a way so for the specific purpose only. So people want to transport the electrons, so you require iron, because not only that iron, but iron 3, iron 2 redox couplate should be very close to 0 so that you can interconvert it when it is required. Okay. So now zinc is also a very good Lewis acid. So in that they act as a hydrolysis. So just I wanted to mention on this slide that this is required, how the metal ions are required for specific purpose. So nature has only all created. So if you want to design some medicine out of it, so you have to be inspired by the nature. Okay. So like what are the different types of roles that I have given. So metallo-biomolecules can be divided into proteins and non-proteins. Then proteins, they transport and storage, and what are the different electron carriers, the cytochromes, iron sulfur. Then metal management, like how to store the metal, how to transfer the metal into the cells. Then oxygen management, how can I do it? Management like how can I transfer the oxygen from to the cell. And now there are the storage and transport, the photoredox and the chlorophyll, it activated by the red light. activated by the red light and for water split injection is very, very important. And these are the enzymes, there is a biological catalyst. So these kind of various kind of enzymatic reactions in the biological system. Now we come to the design of metal-based medicines. So what are the aspects that you should think? So this is the metal, let's say these are the ligands. Most important thing is that coordination number, it ranges from 2 to 10. And then you come to oxidation state, it ranges from 0 to 7. So iron, if you can use the iron, then iron itself, if you design the ligand in such a way, so you can have iron 2, you can have iron 3, and if you design the ligand in such a way, you can stabilize the even iron 4 also. Okay? And then you can see the metal wide range of then redox nuclear stability and the redox potential. Redox potential of the metal is a very, very important. Okay? And then this is the type of ligand how can design to have for biological purpose. So if we end up with a mixing of all these things, then we have the active complexes and active elements, and then it can roll as a functional metal. So this metal ion can for enzymatic reactions. Structural properties, it can give the structure to rigidity to the bioinorganic system. Then it can carry the ligands to the system like the oxygen carriers. Then catalyst, as I told, metalloenzymes, and then the photoactive like a chlorophyll, what is doing the water splitting reactions. So photoactivity is there. Okay. So now this is the periodic table. Okay. So in this periodic table, so different type of metals, not all the metals have the role in the biological system, only very few specific. So scientists are inspired by the nature to devise some of the metal based drugs. Okay, for example, let's say platinum based drug is cisplatin, you know that it is already marketed and it is FDA approved in 1979, and this is against the very good acting very good against the prostate and the ovarian cancer. So what it is doing, it goes and bind to the nuclear DNA and do some anti-cancer activity. And then oranophine. Okay, so this is the structure of oranophine, gold based, that is also used for rheumatoid arthritis, and nowadays people are exploiting this oranophine for anti-cancer activity. And this is the bleomycins, a natural anti-tumor antibiotics that is already present in the nature. So you can exploit it, and they binds very good to the iron 2 in the what is already present in the cell, and do some redox chemistry to generate the hydroxyl radical to cleave the DNA and do some anti-cancer activity. And then see lanthanides, how they can use. These lanthanides are very good MRI agents. So this is a good picture of the MRI. This one you can see. You can image your everything in your body. This MRI agent. So metal is liquid. It is already marketed drugs. And this is a ruthenium based drug. So already this is in the clinical trials for anti-cancer activity. So I will be going a little bit of more detail in that in the preceding slide. So this is the classes of metallo drugs. So they are inert metal complexes that can be GSK3 beta inhibitors, like these GSK3 beta inhibitors. They are actually found during the metastasis of the cancer. So these can be used as anti-metastatic agents, inert metal complexes. Then reactive metal complexes that generate superoxide radicals or hydroxyl radicals, okay, in the cellular redox system. So you can utilize this phenomenon to have anti-cancer activity. Then like these metal complex fragments, they go and bind to the first they deactivate activated into some different compound, and then go and bind to the nuclear DNA and do some anti-cancer activity. For example, is that cisplatin. Okay. So like this, you can classify the different kind of metal products. Okay. So my objective is not to cover all those things, so it cannot be possible. So you require another GIAN course to conduct all the metals and medicines. Okay. So I cannot cover it up all. So I just concentrate on the cancer. Little bit of very brief about the cancer. So how the metal-based drugs can be used to treat a cancer. Okay, so it is a very new, after the discovery of the cisplatin only, this field is explored systematically. Okay, so now so what is the problem with the cancer? So it is still a challenge. Okay, so effective treatment of the cancer is still not available. It is still an elusive goal. So the figure itself tell you how the danger it is. Okay, so that death due to the cancer, it is increasing day by day. Now you can imagine around 20 years back, the polio was frequently found in our societies, polio patients. Okay, now you can find it zero, almost zero. Okay, no polio patients can be found. Why? Because that effective vaccination, it is given and properly implemented. Okay, but for cancer, what is the problem? The cancer we cannot eradicate completely because it is much more complicated and much more challenging, and it has different aspects of the proper drug designing it is required. Okay. So although there are very different type of treatment modalities are there. First is the surgery. If you have some tumors, just surgically you can remove the tumor, or you can radiation therapy. You can put high energy radiations to kill the disease cells, and then you have chemotherapy. Okay, you treat with some drugs and then see after some time your tumor is not there. And there is recently it is emerging up, so it is a immunotherapy. So it is just triggering the immune cells in such a way so that they can itself act against the tumors. Okay, so now we will concentrate only on the chemotherapy. Okay, and there is always a problem with associated with. And you know what is the problem with the surgical. So if you surgically remove also, after some time also you can end up with some cancer tumors. Then for radiation therapy we require a high dose of radiation that induces a secondary malignancy. And then for chemotherapy, the systemic side effects are there. The chemotherapeutic drugs goes, and if you don't know the proper pharmacology of these drugs, then it can go store in the kidneys, store in the livers, and end up with some different kind of toxicities. So systemic toxicities are there. Okay? So we have to tackle all these challenges. So now this is the cisplatin. Okay, so this is the FDA approved in 1979, and this is almost we can say after discovery of polypeptide complex of ruthenium. So cisplatin was the most effective drug that is found against the cancer. Okay, so this is the very simple structure, and you can see there is no carbon. Okay, there is no carbon. This is the only metal with some ammonia and then chloride. So these found very effective against various kind of cancer cell lines. Okay, initially when it was discovered, so it was amazed the scientific community to prompt the research, prompted the research in this area. Okay, so what it actually is doing, go and bind to the nuclear DNA, guanosine G7 position, it go and cross-link, and when it cross-links, so several biochemical phenomena that is occurring to induce the cell death. So here it is a complete picture of this cell and how the cisplatin can work. You can see there is a 4 to 12 millimolar concentration of chloride inside the cell, and there is a 100 millimolar concentration. Once it is inside the cell, the concentration gradient, less chloride concentration will facilitate the chloride removal, and quick acquisition it is happening. On the quick acquisition it is happened, it goes and to the nucleus and cross-link to the nuclear DNA. So after that what is happening? DNA damage, cell cycle arrest. If DNA repair is not possible, then you have a different kind of apoptosis or necrotic cell death. And if DNA repair is still there, cell can survive. Okay, so this is the basic mechanism of the cisplatin, but it has some problem. Okay, what is the problem? So once it is inside the cell, there are different kind of reducing thiols. The thiols can reduce your metal ion. Okay, or the platinum, they can bind to these thiols, and before it reaches to the DNA, it binds with these thiols and just deactivate it. It cannot reach to the cell at all, to the DNA at all, the nuclear DNA. So when it deactivated, so it requires more and more dose. Even more and more heavy dose of the heavy metals, then what will happen? It goes to some, it is go beyond the tolerable limit and store in the kidneys, and you will end up with a nephrotoxicity. So nephrotoxicity, nausea, this kind of always common problem associated with this kind of platinum, cisplatin. So it is effective, but it's end up with serious side effects. Okay. So what we have to do? There are several strategies that you can do. Just slow the rate of the acquisition. Okay. So it should take some time to reach to the nucleus DNA. You have to keep some time. Let's say 10 hours, 12 hours, whatever is the time is required. But if it is so fast, acquisition is so fast, then there itself there is a activated complex. It go and bind to the thiols and that's deactivated. So you have to keep sufficient time. So what you can do? So here it comes with second generation of platinum-based anti-cancer drugs. So it is found that if a chloride is replaced by this kind of diacids like malonic esters and all these things. So and this picoline induces some of the steric effect in around the platinum. Then there is a rate of the acquisition. It is a very slow. That means you are giving enough time for the cisplatin to reach to the target site. Target site, what is the target site? Target site is a nuclear DNA. So in that case it is found it out with this kind of second generation platinum based drugs, they have less nephrotoxicity and equally active. So these are the strategies as second generation and then third generation of anti-cancer platinum based anti-cancer drugs have been discovered. But most interestingly, I can see the use of totally non-toxic, unreactive product platinum 4 product system. So what is that? So earlier it was a implements. It is a platinum 4. Platinum 4 usually it is not active as platinum 2. So it is a stable one. And if you some dihydrox of this platinum complex, it is also clinical trial, and it is also not so active as a cisplatin, but it has a much reduced side effects. Okay. But you have to have some active agent with a less side effects. So then satraplatin was discovered, and instead of this OH it is replaced by the acetate. And how it works? It is like this. When it is incorporated in the cells, the cells have a glutathione. Glutathione is reducing agent. So they can reduce the platinum 4 to platinum 2. Now this platinum 2 can cross-link your DNA, okay, and do some anti-cancer activity. So are actually incorporating some non-toxic platinum 4 products, that is called product, that is not active, but it is activated when during the process. So it is a product. So thyroid deactivation, that is this significantly reduced. Okay, and you also have less side effects compared to the first generation platinum based drugs. Okay, and another important aspect is that if you see the chemistry here, from here to here, 2 axial ligands here, acetates, that are removed. Okay, and this can be a best strategy for targeting and delivering the platinum based drugs. So it is a very important for us to have a targeted chemotherapy. Okay, so how it can be done? So you can see this in example, and this is a platinum 4, and this is this equatorial position that is all occupied by this NH3 and the chloride. And here you can have a targeting molecule, delivery molecule, delivery. Okay, actually delivery molecule. Okay, so what is that targeting molecule? Okay, so cancer cells and the normal cells, they are differentiated with their microenvironments. Okay, so whatever the surroundings, they have some different. Cancer cells have different microenvironment and normal cells have different one. So if we can, what is that mean by that? Different microenvironments, like folic acid receptors, transferrin receptors. Okay, so they are found more in quantity in the cancer cells than in normal cells. Because why? Cancer cells are dividing faster. They require more nutrients. Okay, so therefore receptors are more in quantity. Okay, so we can utilize this fact for targeting our drug into the cancer system, cancer cells. So you can target, like if you target the folic acid here, or they can the folic acid receptor can identify this molecule by the lock and key mechanism, and then by the receptor mediated endocytosis process, it can go inside the cell and then it started working. Okay, and then normal whatever the anti-cancer drugs they are doing it, reduced it in the platinum 2 and then crossed into the DNA. Okay, so this is the fact, and also you can use some delivery molecule. So it is found out that single wall carbon nanotubes, gold nanoparticles, so they are very good delivery agents. Okay, so for currently, for if you want to apply the cisplatin, so you have to intravenous, so you have to give injection in that. Okay, it is no orally available cancer products are available. So earlier, this is the only the first orally available cancer drug that can be orally administered. Okay, and like it has to be delivered properly through the blood. Okay, so you require is something that can deliver well. So carbon nanotubes or gold nanoparticle can be used. So you can attach this gold nanoparticle or carbon nanotube. So simultaneously they target these cancer sites and simultaneously this can deliver well. Okay, so it is that, see, you can see this is the folate receptor, folic acid part. We can recognized by the folic acid receptors, and this is the carbon nanotube and go and binds to the receptors and then internalize into the cells. Okay. So actually, it is found out that the cisplatin, it is 10-fold less, 10-fold more toxic than your cisplatin. So it is, and even it is having very less side effects. So you are able to design some of the platinum-based compounds, platinum-based drugs, anti-cancer drugs that is having more activity and less side effects. So people are working in this direction. Now another example that I can show you how the gold nanoparticle can be used for this same platinum 4 product system. So they have actually found it out that if this platinum loaded this one, so your compound number 1 is just without any receptors or any targeting molecular delivery agent. So this is the IC50 values. It is significantly reduced. It is IC50 value is significantly reduced, means more toxic. So you are able to devise platinum-based product quite effectively. Now people are using this platinum for product strategy in a different way. What is the different way? Now you can see this is the aspirin, right? So why aspirin is required? Cancer is an inflammatory site. When cancer patients is there, so it is always having some pain, always pain, huge pain is there. So patient cannot tolerate this pain. So you need to have some painkillers. So if you can deliver this painkiller in a targeted site itself, so it can act as a dual things. It can also painkiller and also anti-cancer agents. So dual strategy you can develop. So like ibuprofen also you can use, and these are, and for combination therapy, suppose you require to have more activity. So then you require to deliver 2 cytotoxic agents simultaneously. Then how can I do it? So this is the strategy. Here you can drug this anti-cancer drug. It is already attached to the axial position. When it goes to the cell, it is reduced, and these are released in the cell, and along with this platinum 2 drug, platinum 2. This is platinum itself. Then you have some toxicity. Okay, so it is more found to be more toxic. So these way strategically you can make a strategy where you can use the platinum for targeted chemotherapeutic applications. Okay, now go to the platinum. The people are using exhausted with the platinum. Lot of people are doing lot of things with the platinum. Now people are exhausted with the platinum. So now it has to be some alternative strategy, alternative molecules. So why can't we use other metal ions? So like these ruthenium complexes also have been discovered, and they also found to be equally active as a cisplatin. and all these are, some of them are chemical or clinical trials, like this NAMI and this RAPTA, and these are clinical trials. Okay, so how this they impart the anti-cancer activity. The reduction of the ruthenium 3 to ruthenium 2, and when ruthenium 2 is formed, they go and bind to the again guanosine of your DNA. Then it depletes the level of cellular level of glutathione. Glutathione is essential for detoxification of some ROS that is generated during the respiratory process in the mitochondria. So they deplete the glutathione, okay, level, and they induce apoptosis. Then they generate nitric oxide. Okay. Then they reduce the NN bond, where the NN bond double bond is there. No? Any biomolecules, they reduce that one. And then the inhibition of the this reductase, thioredoxin reductase. Okay. So they can work in this way. Then you come to this iridium-based complexes. They are also equally active as a cisplatin and others. So they generate ROS. They oxidize the NADs to NAD plus and oxidize quinone to semiquinone. So all these are happening in the cancer cells when they are applied, and they destroy the cancer cells. And then this is you can see the gold, how the gold can be used for anti-cancer activity. So you can see they use this enzyme, and then they generate ROS to impart cytotoxicity, and they change the mitochondrial membrane potential. If you change the mitochondrial membrane potential, then redox reactions that is happening during the respiration, that is hampered. Okay? In this way you can kill the cancer cells. Now titanium complex, that is people have used that one. So this platinum after hydrolysis, it is totally broken. All the molecules that is broken in the cellular medium, and then there is some receptors are there. So they identify this titanium, go inside the cell, and they bind to the again the DNA and induce the genotoxicity. And now the main topic is that how we can use the green metal. So all this whatever discussed, ruthenium, platinum, iridium, so these are not green metals. These are heavy metals. They are not found naturally. So in the biological system you cannot find them. So for medicinal purpose they have used it, but cannot find it. So if we use these metal ions like manganese is there, iron, cobalt, then nickel, copper, zinc, vanadium, they are already present in the natural system, in the biological system. So if we can use this metal ion for anti-cancer activity, then it will be nice. It is cheaper also, very very cheap. So you can use this metal ion for greener approach. Okay. So how can you do it? Let's say this is iron-based anti-cancer agent. So, and you know this is a ferrocyan, and they actually doing some anti-cancer activity by blocking some enzymes. Okay, and this have been, this is also in clinical trial. And now you can see the bleomycin. So these bleomycin having metal binding arms, so they can bind to the iron and generate the hydroxyl radical, and this hydroxyl radical oxidatively cleave your DNA to impart the cytotoxicity. Okay? And then there is a very classic example how the aminoferrocin based products can be used. Okay? So if we can modify this aminoferrocin based product in this way, so the strategy behind that, design this type of molecule, because hydrogen peroxide is more produced, it is produced in more quantity in cancer cells than in normal cells. Okay, so if we can release effectively aminoferrocin product in the only cancer cells where there is a more and more quantity of hydrogen peroxide, so you may have better anti-cancer activity targeted for targeted chemotherapeutic applications. So what is happening there? You can see this molecule in presence of excess of hydrogen peroxide, they convert into OH, and then it cleaves this part and release the aminoferrocin. Okay, this aminoferrocin along with this quinone method is an anti-cancer drug, anti-cancer agent. So it also shows some anti-cancer activity. And when aminoferrocin is released, aminoferrocin unstable in the biological medium, it releases iron 2. If free iron 2 is there, they readily react with the molecular oxygen to generate the hydroxyl radical, and this hydroxyl radical cleave the DNA. clip the oxidize any biomolecules that is present in the cell. So it can induce the oxidative stress, excess of oxidative stress, that is inducing ultimately apoptosis. So this is the strategy. This is a very nice example where the aminoferrocin based drug can be used effectively as a targeted chemotherapeutic application. And now another way of targeted chemotherapeutic application is that use the light. Okay, let's say you have your drug that is not active in the native state. Okay, but if you activate this molecule with the light, then it undergoes some chemical reaction so that it generates some of the toxic components. Toxic components means like it can be ROS, it can be your any nitric oxide, it can be your organic fragments. Okay, so they can effectively kill the oxidize the biomolecules. So here the PDT is not a very new thing. In 1984 it is discovered. So what they have used, the photofrin is the FDA approved drug, photofrin. So what they have the two different bands. One band is in the solid band, another in Q band. Q band is found in around 630 nanometer. So we excite this molecule to 630 nanometer light. Then by effective intersystem crossing, it goes to the triplet state, and then triplet state it takes the triplet oxygen to convert singlet oxygen. This is a very, very toxic ROS, and it can induces the oxidative damage of the cellular components. Okay, or it can convert it into the hydroxyl radical, that is also very toxic ROS. So this phenomenon is happening here. So what they will use is, suppose you have tumors here. Now the drug is injected and accumulated in the tumor region. Now with the laser light, you can just find that where the drugs are there, tumors are there, where the drugs are accumulated. Okay, and then singlet oxygen is generated or ROS is generated and kill the cancer cells. So you can end up with a very less amount of tumors is present now. So this is a very good strategy for using the visible light as a temporal control, so that you can have effective targeted chemotherapeutic applications. Now you can see that this, you can see this picture. So why use the red light? It is a very, very important question that is asked. It is found out that around more the more wavelength the light is, more is the penetration of this light into the deeper into the cell. Okay. So for tumors, that is the mass of the cells, disease cells. So these tumors, the light has to reach there. It is very, very important. So you need to have therefore get a higher wavelength light. Not only that one, but it is also less toxic. If you use a UV light, so you end up with thymine dimer, and it can induce the genotoxicity. Okay, so you cannot use a UV light or shorter wavelength light. So you must have 630 nanometer light. So the problem is that using the photoframe, so it is actually degraded into, when it is comes to the liver, it degraded into bilirubin, and bilirubin creates jaundice. It induces jaundice. So it is a side effect, one of the side effects. And in the skin, and all the process in the photodynamic process, it has to be carried out in the dark. Okay. Now, if you just patient is taken exposed to the sunlight, now the drug is still there, it start acting. Whatever the drug component is present in the normal cells also, they start activating. Okay, and then create the normal tissues also. So it is not useful for PDT application. So therefore, it has a very limitation now. The clinically that is almost it is no longer in use. So you have to make it this process effective. So why the metal complex is important, particularly the transition metal, copper complex, iron complex, and when copper you make it an appropriate ligand, then you can have the visible light absorption. So these can absorb around 500 to around 700 nanometer. You can design some ligands such that the complex can absorb in this region. So you can use this light for its applications for metal based drug. And for iron also it is same thing. They are absorbing either charge sulfur transitions or DD transitions, whatever it is. So they are absorbing in red light region. So that is the light we require. Okay. So these are the common factors that we have to look into for photoactivated chemotherapy applications. Most important is that the toxicity in the dark and the toxicity in the light, that should have drastic difference. Okay, so this is a very, very important. Most important things that you have to consider for PDT applications. Now, what is happening in the metal complex? Let's say this is a transition metal complex, and this is octahedral complex. You can see, and these are the MOs. You can see the different type of electronic transitions. Okay, metal center transitions, then LMCT or MLCT or LMCT transitions, and then ligand center transitions. So you can explore these transitions for phototherapeutic applications. And when the molecules get excited, they can undergo various kind of reactions. So like the photophysical reactivation, then energy transfer process, then ligand exchange reactions, then isomerization within ligand itself, and then photodegradation. Photodegrades to release some of the active component. And these strategies have been utilized by the Professor Sadler. And they have made this platinum azide complex, and when it photoexcite with some visible light, they found this azide is released. Okay, azide is released, and you are making in situ a platinum 2 complex, and that again cross-link into the DNA. Okay, so in this way, photoactivation takes place, and you are making some active platinum 2 compound, and for anti-cancer activity. Okay. And this is another classic example of Professor CSIR-CSMCRI has developed this one. This is a platinum 2 complex again, and there is some photoactive matter that is a naturally active ingredient, that is called curcumin. Okay? And this curcumin is photoactivated, and this bond length, it is increased, and ultimately leads to dissociation, and this vacant position is created. It is no longer become vacant, it goes bind to the nucleus, DNA in the nucleus. So, and they have found very good activity against these cells, against various type of cancer cell lines. And these are some photoactivated chemotherapeutic applications. Green metals, like you can see, the copper they are used for photoactivated chemotherapeutic applications using these ligands. There is iron, it goes to the nucleus and then do some toxicities in that. And then this is a copper complex again with the curcumin, and this is the BZ complex that is also shows very dramatic photoactivated chemotherapeutic properties. And what we have done in our lab, so we made this type of complexes and explore for the photocytotoxicity. Okay. So, and these are the results. You can see here. The complex 1B in the visible light, that is 17, and the dark it is 30. So we are able to get almost half cytotoxicity. It is increased in the light in complex number 3, which is the most active one. So although this data is not so promising, but at least we are able to get some complexes that can have photochemotherapeutic applications. So we are designing some of the better metal-based photochemotherapeutic agents. So, and this again we find it out that where this apoptosis is occurring in the cells, and nucleosome DNA fragmentation studies also revealing that this fact apoptosis, and ROS is generated, and so we have done the DCFTA assay, so in which DCFTA, when it is exposed to the ROS, then it clipped, and from a fluorescent dichlorofluorescent molecule and gives a green fluorescence. So more and more is the ROS generation, means more and more green will be coming, and if you do the FACS, the fluorescent intensity of this green fluorescence, it will increase more further. So you can see here that is black one is in the cell only, in the cell plus DCFTA some fluorescence, and in the dark one if put it with the complex in the dark. Although we have shown in some cytotoxicity, they seep little bit. It means they have increased the ROS level to some extent. And even if we just shine the light in green light, there is a more enhanced generation of similar ROS. Okay, and this ROS generation from the complex is also studied by the invisible and also the EPR spectroscopy. Okay, so actually the process is that, and this complex when you extract water they undergo decarboxylation. Okay, and decarboxylation leads to generate RN2, and then RN2 reacts with the molecular oxygen or hydrogen peroxide in a cell to generate this hydroxyl radical. Actually, this is hydroxyl radical. It's responsible for cell damage. Okay, and this is again the copper complex, new copper complexes that we have designed, and they have shown very promising anti-cancer activity. And these are the results. So you can see for copper, it is 0.8 micromolar, complex number 4. If you can go back, this pyrenyl complex of 0.8 micromolar at a sub-micromolar level, and it is almost 10 times more cytotoxic than whatever is in the dark. Copper is usually normally cytotoxic because copper 2 when it is exposed to the cells, they are in situ converted into copper 1 by the cellular glutathione. Okay, reduced to cellular glutathione. And then copper 1 is produced and then takes up the molecular oxygen and then converted into hydroxyl radical. So in a dark cell, copper 2 complexes are active. But if we can make it more active when exposed to the light, okay. And then we have done the cancer cell specificity studies. So what we have done, around 5 micromolar, we treated the complex with 4 micromolar, and this is the HeLa cells, and this is the 3T3 cells, and this is actually the normal cells. You can see compared to the normal cells, this one. This is the 3T3 cells, and you can see that in HeLa cells, and it is more active compared to the normal cells. That means it has some tumor specificity. This complex is some tumor specificity. So again, we have done the cellular localization studies because the pyrenyl complex, it is a fluorescence compound, and we can visualize the compound inside the cell. It is cytosolic, mainly cytosolic localization. And then the ROS is also detected when it is visible light. When it is exposed to the visible light, more and more ROS is generated. That is by DCFD experiments have been compound, and we have further then what is the ROS species, what is the nature of ROS species. So we have done this DPBA experiment. So this compound, when it is react with singlet oxygen they produce, they undergo this type of 2+2 cyclization reactions, and they convert in this one. So absorbance of this one is supposed to decrease. Okay, so we have done this experiment. So what is there with the time, with the exposure of the visible light, you can see more and more decrease in the intensity of this band. So that means more and more singlet oxygen generated with time when you exposed to the visible light. And this you can see compared with the data. The extent of decrease in the fluorescence intensity of this TPPA, it is more in case of pyridine, and then it is another compound, control compound we made it. You can see compared to, if we can compare these two results. So this one is for pyrenyl and this is without pyridine. So in pyridine complex there is a more and more increased generation of singlet oxygen, and these are the controlled experiments. So to account theoretically to account for this singlet oxygen generation, we have done again DFT and TPFT calculation, and we have found it out that for complex number 3, that is without any pyrenyl, so these triplet excited states, and this is a doublet down state, and for the complex, and there are triplet excited, that is a far in energy, that is a far more in energy. So so intersystem crossing is not effective here, but in this pyrenyl complex, these triplet states are relatively with a high coupling, spin orbit coupling constant values, they are relatively lower in energy, so it is effectively under the intersystem crossing. So if it is intersystem crossing is better, then there is a more that triplet oxygen is converted into singlet oxygen. So this account for the singlet oxygen generation in case of complex number 4, pyrenyl complex, compared to the without pyridine complex with the pyridine. Okay. So may I come to the summary and conclusion. So whatever, this is a more and more like a more example I have given for what people have done already, like platinum complex, how they strategically you can make the platinum complex effective against the cancer, and then how can you use the other metal ions for anti-cancer therapy, and how you can use the visible light or light for temporal control to generation of the ROS species for effective targeted chemotherapeutic applications. And briefly I just discuss about my work also. So in this GIAN lecture. So then ultimately I want to thank Dr. Chandisi Malakar so for giving me opportunity to talk in this prestigious GIAN course, and I want to also thank David Singh and ACRB for financial support, and then Professor CSIR-CSMCRI for collaborative work, and my present lab member Dulal, Vinita, Vandana and Reena. Okay, thank you very much. So if there is any questions, I can.
There are a number of anti-cancerous substances, both in research and development stage and also in clinical market. What we see that most of these are basically organic in nature.
Yes, yes.
Metals are not.
Yes.
So if we compare these two types of segments, metal containing anti-cancerous and only purely organic compounds, in which case do you expect that the toxicity will be lesser? Expected to be lesser?
So that is a very good question actually. So toxicity, it depends. Means like many organic compounds will find it that is a very toxic, and even they can find it out in a nanomolar level toxicity. But all the cancerous drugs we will see, so they have some little bit of non-specific. These drugs are mostly non-specific. They do not go and bind to the targeting the tumors. So both in the metal-based drugs and also organic-based drugs. So now the second generation or next generation cancer drugs, it will be how you can make it more targeting. So if you can more targeting, whether it is metal-based or organic-based, so that drug will be effective more. So at this stage, exploration of the metal-based drugs is a very nascent stage now. So it is not done extensively done yet. But whatever the drugs, it is already there. Like cisplatin, you can see it is having very toxicity. Nephrotoxicity is huge. So now people have not started using this cisplatin no more. So carboplatin and then another drug, it has come up. So these also have some side effects. Okay. Now if we can see the photochemotherapeutic application. Now the problem is that you can minimize the toxicity, but the problem is how to bring the light to the tumor site. It is a very challenging task for PDD applications. But if you can devise of this technology, then I think it can be a future perspective for anti-cancer designing. Because I know Apollo Hospital in the Chennai, they have used some of the iron oxides for photothermal applications. Okay. So they have device, they took the light to the tumor sites, and they effectively shown that it is a very good anti-cancer agents targeted for targeted chemotherapeutic application. So at this stage, for metal-based drugs, we cannot answer your question. So whether it is more one and whether it is less one, but at least you can have some alternative.
Because what we have seen in most of the cases, that suppose some drug we have taken, the drug has done its whatever it is supposed to do, that has done. After that, some byproduct whichever is produced in the body itself.
Yes.
Generally, if it is not containing any metal, then excretion part becomes a little easier.
Yes.
If we consider the profile of the material.
For heavy metals, if you think for heavy metals one like platinum, that is the problem, and it is not easily excreted. That's what platinum having huge nephrotoxicity problem. And also the ruthenium, that is also in the clinical trials, they are also having facing these kind of problems. So it is very difficult to excrete from our system. So that it is going to store in the kidneys. Okay, and some of it is found it out that heavy metals are also some go and store in the brain also. Okay, so this is a very difficult task. I mean, that's what I am telling. So these are not the green metals. Okay, so if you can use iron, so let's say it is degrade, it is degrade also. Then iron, there is a system, the iron can be stored. It's like if you can take more like iron capsules, it doesn't harm. Means like,
Yeah.
but to some extent it is there.
Yes. Here what I'm not actually much acquainted to that part. Just what I have seen in the literature, that probably suppose the case of iron or calcium, even if it goes to beyond certain
Yes,
extent,
yes, yes.
it can create
It can create a problem.
especially
Right,
problem.
right.
And especially for the males, it is much more problematic because there is no specific way to extract the excess part of it.
Yes, yes.
So even if we convert it into iron or maybe other transition or comparatively other metals, not the heavy metals, then my question is that how far we can go up to how far we can consider this one,
Yeah,
considering the safety matter.
Right. So we cannot tell it is up to this much. So these kind of questions are frequently asked by the referees. So if you are asking, telling this iron is biocompatible, it's already present in the nature, molecule, but also to some extent it has become toxic. Okay, but if you can design a molecules like let's say iron complex, let's say like photoactivated chemotherapeutic applications, let's say in 1 macromolar in HeLa cells, like in normal cells, cancer cells, it is IC50 value, it is cell is killed to the extent of let's say 90% cell is killed, but at the same concentration if you put it in the dark, 90% cells survive. Okay, so that means by putting that IC50, let's say around 1 macromolar range, you are able to kill the cancer cells by using light by 90%, but where only 10% cell is affected in the dark. Then you can with the 1 micromolar concentration, that is not harmful at all for iron. Okay, so you can make use of like this one. So that's what I just given one data like cancer cell specificity. You just compare the cell survival data against the normal cells and against the cancer cells. Okay, so that's what it is promising. We can find it out that IC50 value in the cancer cell it is less, and IC50 value in the normal cell it is more. And we took the concentration, same concentration. Let's say the IC50 value of the light. At this concentration, we can find it out 50% cell is killed for the light. And now at the same concentration, 90% normal cell is surviving. Okay, so these we will try to explain some of the facts. But I think we need still more studies on this direction, how to make it more targeted. Still.
Thank you.
So you are talking about green metals. How these metals are green?
Okay, so green metals are like say, if you can use platinum, if you can compare platinum and iron, which one is a more means preferred metal? Iron is the most preferred metal, right? Why it is so? If we want to make it of something of iron, that is more cheaper, right? It is more cheaper than platinum. And if you want to use in our system, platinum is more harmful than iron. So in this respect, we can tell this iron is a more greener compared to your platinum, heavy metals, like that.
Only vanadium to zinc, these are the only green metals.
We can say some to extent green metals, but you cannot use it in much more excess. So these excess, because you can see, I just showed you one slide, only less than 0.1% of this total composition of our body, it is containing the metals. Now you can see what is the amount, stoichiometric amount. It is a very, very less. Now you can say Dr. Chandi, and now he is also doing how many more percentage of metal salt you are using for catalytic purpose, like say 10 more percent, 5 more percent, 1 more percent. So far you can go less. So that is the catalytic amount is required. So here also they are doing some catalytic catalysis. So you require a very less quantity. Okay. Even at this less quantity also platinum, ruthenium, they are very dangerous. Okay. They are having some side effects. So,
In our first generation, you have used singlet oxygen.
yes.
Why? It's only
Okay.
single, not
So-
triplet.
Okay.
I just want to see that slide.
This one?
No, this one.
This one? Okay. So in this way, ROS it can be different type. In the previous paper, iron it is we have found out that the hydroxyl radical is there. We have EPR proof because EPR DMP, it forms an adapt with the OH hydroxyl radical and it gives a 4-line split spectra, EPR spectrum. We have detected that one. That is hydroxyl radical. Now, if you can consider this one, this copper-based complex, we found out it is singlet oxygen. It is not the hydroxyl radical, but something ROS is there. But to know the nature, okay, so then what we have done, we have taken this. This is a well-known quencher of singlet oxygen. Okay, so we have done this experiment. We found it out. It is drastically reducing when you shine the light in presence of the DPBF and complex. The intensity of the DPBF is decreasing significantly in presence of complex when you shine the light. Without light, it is nothing is happening. Okay, with light, it is decreasing. So that means when you shine the light, singlet oxygen is generated, and this generated singlet oxygen is trapped by this molecule, and the intensity is decreased. So this way you explain. And after getting these points, then we try to do it because there are other literature also there. Because copper complexes, they have other indirect ways. Okay, indirect ways they prove that okay, copper complexes they use singlet oxygen as a cytotoxic species. Then I told Dulal, okay, so let's use it for theoretical calculation, do theoretical calculation, how the energetics can be compared. And he just compared, and it is find it out that in case of complex number 3, and if you can see the data here, very interesting one. And this is your complex number 3, and this is number complex number 4. That means complex number 3 without pyridine, okay, it is not giving so much, generating so much singlet oxygen, but with pyridine it is generating huge amount of singlet oxygen. But what is the reason is that? To find it out the reason, we have done this theoretical calculation, and we find that complex number 3 means like if you can see a type 2 process, so it has to be doublet to triplet excited states must be, some triplet states must be there, but doublet to triplet it is spin forbidden. The transition is a spin forbidden, that you cannot do it. But if there is some low line triplet states which undergo intersystem crossing, as you have seen in PDT, photofilm, okay. Here also the ground state is a doublet, and we have found that some triplet states are there that is energetically much more higher excited states. Okay, so these excited states, so since to promotion of these excited states, doublet excited state to the triplet excited state, it is quite impossible. It is not possible. But when it to the 4, complex number 4, we have found it out that these triplet excited states with the high spin orbit coupling constant values, they are energetically lower, and from doublet excited state to triplet state, intersystem crossing is quite favorable. We just done it qualitatively. Quantitatively we cannot do it. We couldn't do it. But qualitatively we just prove it. It undergo intersystem crossing. It is possible. When it comes to intersystem crossing, then it reacts with triplet oxygen. Triplet to triplet oxygen is triplet reaction with the triplet state with triplet oxygen. It is spin allowed. So it can undergo and it convert into singlet oxygen. Energy, we calculate the energy that is required, and it is exactly matching with the singlet oxygen conversion. Okay, so that's what. Okay, if there is any more questions, then I am always there. Okay, so thank you very much for your kind patience. Thank you. Okay, so Dr. Chandi is not here, so has given some assignments to work it up. You can come.
Better to dictate. I'll dictate the questions. You can make a note of it. Mention any green brominating agent for organic compounds. Mention any green brominating agent for organic compounds. Yeah, green brominating agent, which carries 10 marks.
Mention any green brominating agent
For organic compounds. You want me to repeat? Mention any green brominating agent for organic compounds. Right? Second one, draw the mechanism of its conversion. So I'll write the substrate. Clear? Converting a vinyl into acidic group. Everybody can see.
What is the question?
Write the mechanism for this. How you can bring about this change? Write the mechanism. Yes. So if it has 3 steps, we have to mention mechanism for each step, which carries 10 marks. Third question. Discuss the novel alternate of CC and CX bond formation. Discuss the novel alternate of Discuss the novel alternate of CC and CX bond formation. Alternate of CC and CX bond formation. X. In compared to traditional method. Mention the advantages and disadvantages.
Only one method or more? How many?
You have more, you write it more. I'll repeat once again. Discuss the novel alternate of CC and CX bond formation in compared to traditional method. Mention the advantages and disadvantages. Carries 10 marks. Can I report this? Mention any green reagent for the above transformation. So convert phenol to catechol. Mention any green reagent for the above transformation. Show the application. What's the application of that reagent?
Mention any green reagent
For the above transformation. For the above transformation, show the application. Show the application.
Repeat.
Yeah. Mention any green reagent for the above transformation. Reagent for the transformation. Show the application of the product in synthesis of heterocycles. In the synthesis of heterocycles. Mention any green reagent for the above transformation. Whatever I mentioned the transformation. Show the application of the product in synthesis of heterocycles. Carries 10 marks. And the last one, how platinum 4 can be used for? Show the application of the product in synthesis of heterocycles. Last question, how platinum 4 can be used for targeted chemotherapy. Targeted chemotherapy. Targeted chemotherapy. 10 marks. So 5 questions, 10 marks each.
Last question.
How platinum 4 can be used for targeted chemotherapy. Done?
हो गया ना